Right now, at this very moment, a sphere of incandescent plasma 109 times wider than the Earth is burning through 620 million metric tons of hydrogen every single second. The temperature at its core reaches 27 million degrees Fahrenheit, a heat so extreme that if you could somehow transport a pinhead-sized sample of that core material to the Earth's surface, it would kill every living thing within 1,000 miles before it even touched the ground. The light leaving that sphere right now will travel 150 million kilometers before it strikes your face approximately 8 minutes from now. You will feel its warmth without understanding what produced it. Yet when you picture the sun, you picture something gentle, something small, a yellow disk hanging in a blue sky, pleasant to glance at during a sunset, easily blocked by a raised hand. The image in your head bears almost no resemblance to the actual object. What exists 93 million miles away is not a disk, it is not yellow, it is not small, it is not gentle. It is a thermonuclear engine of such incomprehensible violence that if you could somehow witness its true surface, without the protective filter of distance, your brain would struggle to process what it was seeing. The sun you think you know does not exist. The sun that actually exists is a monster. Here is what will shatter everything you believe about our nearest star. The sun is not merely large. It contains 99.86% of all the mass in the entire solar system. Every planet, every moon, every asteroid, every comet, every grain of dust drifting through the void between worlds, all of it combined represents barely more than a rounding error in the sun's gravitational ledger. Jupiter, the giant that could swallow every other planet and still have room for more, is a speck beside it. Earth is not even a speck. Earth is a mote of dust orbiting a bonfire the size of a city. And yet, within the terrifying scale of this cosmic furnace, lies the only reason you are alive to contemplate it at all. Every atom of warmth you have ever felt, every photosynthetic reaction that has ever produced oxygen for your lungs, every calorie of food energy you have ever consumed, all of it traces back to nuclear fusion reactions occurring in a core so dense that the pressure would crush any substance known to human science into forms we cannot replicate in any laboratory on Earth. The monster is also a mother. The destroyer is also a creator. The sun is the most important object in your existence, and you have almost certainly never understood what it actually is. If you want to discover the true scale of our star and enjoy this type of content, then please consider liking and subscribing. It truly helps more than you know. Are you ready? Let us begin. The problem starts with your eyes. Human vision evolved on the African savanna to track predators, find fruit, recognize faces, and navigate terrain. It did not evolve to comprehend astronomical scales. When you look at the sun, through appropriate eye protection, because even a brief unfiltered glance can permanently damage your retinas, you see a flat disk approximately half a degree across in the sky. This is the same angular size as the moon, a coincidence so statistically improbable that it enabled the total solar eclipses which have shaped human religion and science for millennia. But angular size tells you nothing about actual size. The moon is 2,160 miles in diameter. The sun is 864,000 miles in diameter. They appear identical in the sky because the moon is 400 times closer. Your eyes cannot feel the difference between an object that is nearby and small and an object that is far away and immense. They see the same half-degree disk. This perceptual limitation means that every time you have looked at the sun, your brain has been lying to you. It has been categorizing the sun alongside other circular objects in your experience. Dinner plates, soccer balls, the moon, the pupils of eyes watching you. None of these comparisons are remotely accurate. The sun is not a circle. It is a sphere so vast that if you could somehow hollow it out and place the Earth at its center, the moon's entire orbit would fit comfortably inside with room to spare. You could place the Earth in the center of the sun, and the moon could orbit at its normal distance of 239,000 miles, and that orbiting moon would still be nowhere close to touching the sun's surface. The moon would be moving through the middle regions of the solar interior, surrounded on all sides by plasma hundreds of thousands of miles thick in every direction. Let that settle into your mind. The moon's orbit, the entire path the moon traces around the Earth every month, would fit inside the sun. The space between the Earth and the moon, that gulf that humans crossed only once in 1969 and have not crossed since 1972, is insignificant compared to the Sun's radius. You could stack 30 Earths in a line and still not span the Sun's diameter. You could stack 109 Earths across its face. You could fit 1.3 million Earths inside its volume, 1,300,000 Earths. If the Earth were a basketball, the Sun would be a sphere 84 feet in diameter, the height of an 8-story building. If the Earth were a single grain of sand, the Sun would be a ball 3 feet across. No matter what comparison you choose, your brain cannot hold the true scale. Consider what 1,300,000 of anything actually means. If you counted to 1,300,000 at a rate of one number per second, it would take you 15 days of continuous counting without sleep, food, or pause. If those 1,300,000 Earths were people standing in a line, that line would stretch from New York to Los Angeles and back again more than 200 times. The Sun contains enough volume to hold more Earths than there are minutes in 2.5 years, and every single one of those hypothetical Earths would be bathing in temperatures that would vaporize them instantly upon contact with the solar plasma. The number is too large. The human mind did not evolve to process quantities of this magnitude. When ancient humans looked at the Sun, they saw a god, a chariot, a disk of gold, a divine fire. They were not wrong to reach for mythology, because the truth is equally beyond normal comprehension. The only difference between calling the Sun a god and calling the Sun a G-type main sequence star is the system of language you use to describe something your brain cannot actually picture. What makes the Sun's scale even more disorienting is that the Sun is not even particularly large by stellar standards. The Sun is in fact a fairly ordinary star, smaller than average, cooler than average, less luminous than average. The reason it dominates your sky is simply that it happens to be close. The nearest star to our Sun, Proxima Centauri, is a red dwarf so small and dim that despite being only 4 light-years away, you cannot see it without a telescope. Yet even tiny Proxima Centauri dwarfs the Earth beyond imagining, and the largest known stars make our Sun look like a grain of sand beside a basketball. VY Canis Majoris, a red hypergiant in the constellation Canis Major, is approximately 1,420 times the diameter of the Sun. If you placed VY Canis Majoris where the Sun currently sits, its surface would extend past the orbit of Mars, past the asteroid belt, and nearly to the orbit of Jupiter. The Sun, that monster we have been describing, would be a tiny dot somewhere deep inside the hypergiant's outer layers. And yet even VY Canis Majoris is not the largest known star. Stephenson 2-18, another red hypergiant, may be as large as 2,150 times the Sun's diameter. At that scale, if Stephenson 2-18 replaced our Sun, its surface would extend past the orbit of Saturn. The Sun you think of as inconceivably vast is, in cosmic terms, a small yellow dwarf occupying one modest point in an unremarkable arm of a galaxy containing 200 billion other stars. But we're not concerned today with the giants. We're concerned with understanding the Sun as it actually exists, this particular star orbiting this particular galaxy, the star that made your life possible and will continue burning for another 5 billion years before it expands into a red giant and consumes the inner planets in fire. The Sun that will one day kill every form of life on Earth is the same Sun that currently makes all life on Earth possible. This paradox runs through every aspect of solar physics. The Sun gives life and takes it. The Sun is stable and violent. The Sun appears simple and is unimaginably complex. The yellow colour you think you see is a lie told by your atmosphere. The Sun does not emit yellow light. It emits light across the entire visible spectrum, peaking in the blue-green range at a wavelength of around 500 nanometers. If you viewed the Sun from space, away from Earth's atmosphere, you would see a white star with a faint blue-green tinge. The reason it appears yellow from Earth's surface is that our atmosphere scatters shorter wavelengths of light, blue and violet, more efficiently than longer wavelengths. This is why the sky is blue. The blue light from the Sun is being scattered in all directions by atmospheric molecules, reaching your eyes from every part of the sky, rather than just from the Sun's direction. What remains in the direct beam travelling from Sun to your eye is depleted of blue wavelengths, leaving an excess of yellow, orange and red. The lower the Sun sits on the horizon, the more atmosphere its light must traverse, and the more blue light is scattered away. This is why sunsets appear red and orange, not because the sun is changing colour, but because you are seeing the sun's light through a progressively thicker filter of air. So when you picture a yellow sun, you are picturing an atmospheric artifact, a processing error produced by the collision of white light and nitrogen molecules. The actual sun is white. Its surface temperature of approximately 10,000 degrees Fahrenheit produces a thermal spectrum that our eyes perceive as white when viewed without atmospheric interference. Astronauts report this consistently. From space, the sun is blindingly white, with none of the warm yellow tint that earthbound observers associate with it. But the colour is merely the beginning of the deception. The smooth surface you imagine is equally fictitious. When you picture the sun, you probably picture something like a luminous billiard ball, a perfect sphere with a uniform surface, perhaps with a few sunspots scattered across it like blemishes on otherwise smooth skin. This image bears no relationship to reality. The sun's visible surface, the photosphere, is a churning chaos of plasma cells, magnetic field lines, eruptions, and temperature gradients that make Earth's most violent weather systems look like gentle breezes. The photosphere is the layer where the sun becomes opaque to visible light, where the plasma finally becomes thin enough that photons can escape into space, rather than being endlessly absorbed and re-emitted by solar material. Below the photosphere, the sun is opaque, and photons generated in the core may take tens of thousands of years to random walk their way outward through the dense plasma. Above the photosphere, the sun's outer atmosphere becomes progressively thinner and more transparent. The photosphere itself is only about 300 miles thick, a remarkably thin shell around a sphere 400,000 miles in radius. It is in this thin shell that the sun's visible light originates, and this shell is not smooth. It is composed of roughly 4 million structures called granules, each one a convection cell the size of Texas. Picture the surface of boiling water in a pot. The way hot water rises in the centre of each cell, spreads outward across the surface, cools, and sinks at the edges, creating a pattern of polygonal cells separated by darker boundaries. The sun's photosphere displays exactly this pattern at a scale that defies comprehension. Each granule represents a column of hot plasma rising from beneath the photosphere, spreading across the visible surface, and then sinking back down at the edges where it has cooled. The bright centres of the granules are hotter than the darker edges by roughly 300 degrees Fahrenheit. From Earth, with appropriate solar telescopes, these granules are visible as a fine texture across the sun's face, giving it an appearance astronomers describe as resembling rice grains or the texture of an orange peel. But each of those rice grains is larger than many nations. A single solar granule could cover the entire state of Texas, or the entirety of France, or the combined area of both Koreas. Imagine standing in Houston and watching as a pillar of plasma the width of the state rises beneath your feet, carrying you upward at speeds of several thousand miles per hour, spreading across the surface, and then plunging back down into the solar interior at the state's border. Now imagine 4 million of these cells operating simultaneously across the sun's face, each lasting only about 8 to 20 minutes before being replaced by a new cell as the convection pattern shifts. The entire visible surface of the sun is renewed every few minutes. The face you see at noon is composed of entirely different plasma than the face you saw at breakfast. The granulation pattern is constantly churning, boiling, rising, falling, appearing and disappearing in a ceaseless roil of superheated gas. And the granules are merely the smallest scale of this convection. Beneath them lie larger structures called supergranules, convection cells roughly 20,000 miles in diameter, nearly 3 times the width of Earth. These supergranules are not visible directly in white light, but they can be detected through their effects on the sun's magnetic field and through Doppler measurements of the plasma velocities at the solar surface. Within each supergranule, material flows from the centre toward the edges at velocities of roughly 900 miles per hour. At the edges of the supergranules, this material accumulates and sinks, creating a network of boundaries visible in certain wavelengths as the chromospheric network, a honeycomb pattern covering the entire sun. Roughly 30,000 supergranules cover the solar surface at any given time. If the granules are continental in scale, the supergranules are planetary. A single supergranule could swallow the Earth with room to spare. The plasma flows within these cells are enormous rivers of ionized hydrogen and helium, moving at velocities that would carry a car from New York to Los Angeles in 3 hours. And yet even these supergranules are dwarfed by a third level of convection called giant cells, structures roughly 200,000 kilometers across, roughly half the distance from the Earth to the Moon, that are still not fully characterized by solar physicists because their movements are so slow and their boundaries so diffuse that decades of observation have been required to confirm their existence. The Sun's surface is not a surface in any normal sense. It is a layer of continuous violent motion operating at multiple scales simultaneously, a fractal pattern of rising and falling plasma where the smallest visible structures are larger than continents and the largest structures are larger than planetary orbits. And this motion never stops. The Sun has been convecting like this for 4.6 billion years and will continue for another 5 billion years before exhausting its hydrogen fuel. For 10 billion years, the surface will churn with these continental-scale convection cells, never repeating the same pattern twice, each configuration as unique as a fingerprint, and lasting only minutes before being erased by the next. Perhaps nothing demonstrates the true scale of solar activity more viscerally than a sunspot. When you see photographs of sunspots, they appear as small dark blemishes on the solar disk, minor imperfections on an otherwise smooth surface, comparable perhaps to freckles on human skin or spots on a ripe banana. This comparison is catastrophically wrong. A typical sunspot is large enough to swallow the Earth whole. A large sunspot group can extend across a region larger than the distance from Earth to the Moon. The largest sunspot ever recorded, observed in April 1947, was so vast that it could have contained more than a dozen Earths arranged side by side. Sunspots appear dark because they are cooler than the surrounding photosphere, roughly 7,000 degrees Fahrenheit compared to 10,000 degrees in the surrounding plasma. But 7,000 degrees Fahrenheit is still hot enough to vaporize any known substance. If you could somehow extract a sunspot from the Sun and view it in isolation against the blackness of space, it would not appear dark at all. It would glow with a brilliant orange-red light, brighter than any arc welder, brighter than molten steel, bright enough to blind you instantly if you looked at it directly. Sunspots appear dark only by contrast with their even brighter surroundings. They're relatively cool shadows in an ocean of fire. The reason sunspots are cooler than the surrounding photosphere has to do with the Sun's magnetic field, and this begins to hint at the true complexity of solar physics. The Sun is not merely a ball of burning gas. It is a ball of plasma, ionized gas in which electrons have been stripped from their parent atoms, leaving a soup of positively charged nuclei and negatively charged electrons moving independently. Plasma behaves differently from ordinary gas in one crucial respect. It interacts with magnetic fields. Charged particles spiral around magnetic field lines, trapped by the field and unable to move freely across it. Where magnetic fields are strong, plasma motion is suppressed. Where magnetic fields are weak, plasma moves freely. Sunspots form where intense magnetic field lines punch through the photosphere from the solar interior, creating regions where the normal convective motion of plasma is inhibited. The hot plasma cannot rise efficiently into these regions because the magnetic field resists the movement of charged particles across its lines of force. With less hot plasma reaching the surface, the region cools relative to its surroundings. The result is a sunspot, a region of suppressed convection where concentrated magnetic fields have created a relatively cool island in the photosphere. The magnetic field strengths in sunspots are staggering. The Earth's magnetic field at the surface is roughly half a Gauss, strong enough to deflect a compass needle but imperceptible to human senses. The magnetic field in a typical sunspot is 2,000 to 4,000 Gauss, roughly 4,000 to 8,000 times stronger than Earth's field at the surface. In the most intense sunspot cores, field strengths can exceed 6,000 Gauss. These magnetic fields contain enormous amounts of energy, and that energy can be released in sudden, violent events that dwarf anything in human experience. The structure of a sunspot visible through a solar telescope is itself a study in planetary scale. A typical mature sunspot consists of two distinct regions, a dark central zone called the umbra, and a surrounding lighter region called the penumbra. The umbra is the coolest part of the sunspot, where the magnetic field is strongest and most vertical. The penumbra is a region of intermediate temperature, where the magnetic field is inclined at an angle to the surface, allowing some convective motion, but not as much as in the surrounding undisturbed photosphere. Through high-resolution solar telescopes, the penumbra displays a spectacular filamentary structure, bright and dark radial streaks created by channeled plasma flows along inclined magnetic field lines. These penumbral filaments are individual plasma structures roughly 200 miles wide and thousands of miles long, rivers of glowing gas flowing outward from the sunspot umbra along magnetic channels. Let the scale settle into your understanding. The individual filaments in a sunspot's penumbra, the fine structure visible only through specialized solar telescopes, are each 200 miles wide. 200 miles is the driving distance from Los Angeles to Las Vegas. A single strand in the fine texture of a sunspot's edge spans that distance, and there are hundreds of such filaments in a typical sunspot penumbra, all flowing outward in parallel streams, carrying millions of tons of plasma per second away from the sunspot core. The sunspot penumbra alone, just the outer fringe of the dark spot, would cover a significant fraction of the Earth's surface if superimposed upon it. The umbra, the dark core, is where the monster truly reveals itself. A large sunspot umbra can be 30,000 miles in diameter or more, nearly 4 times the diameter of Earth. If you place the Earth in the centre of such an umbra, you would need to drive more than 8,000 miles in any direction before you reach the edge, equivalent to driving from New York to Beijing, and then continuing on for another 3,000 miles. You would drive from dawn to dusk for weeks before escaping the shadow of a single sunspot. And that sunspot, that continentally scaled region of cooled plasma and concentrated magnetism, would be just one dark blemish among dozens that might be scattered across the sun's face during periods of high solar activity. During solar maximum, when the sun's 11-year activity cycle reaches its peak, the solar disk can be peppered with dozens of sunspot groups simultaneously. Some of these groups can contain hundreds of individual spots of various sizes, from tiny pores barely resolved by Earth-based telescopes to massive complex regions that could engulf Jupiter's Great Red Spot many times over. The total area covered by sunspots during solar maximum can exceed 0.5% of the visible solar disk. 0.5% sounds small until you calculate what that means in absolute terms. 0.5% of the Sun's visible surface is approximately 2.3 billion square miles, roughly 20 times the total surface area of Earth. During active periods, the Sun's cool, dark spots alone contain enough area to hold 20 Earths with room to spare. But sunspots are not merely static dark regions. They evolve, migrate, rotate, merge, split, and eventually dissolve over timescales of days to weeks. The new sunspot typically emerges as a tiny dark pore, barely visible against the granulation. Over hours to days, it grows as more magnetic flux emerges from beneath the photosphere, eventually developing the umbral penumbral structure of a mature spot. It will then persist for days to weeks, depending on its size and the complexity of the surrounding magnetic field. Throughout its lifetime, it will participate in the Sun's differential rotation, moving faster near the equator than near the poles because the Sun, being made of plasma rather than solid matter, does not rotate as a rigid body. Near the solar equator, the photosphere rotates once every 25 Earth days. Near the poles, the rotation period extends to roughly 36 days. This differential rotation shears the Sun's magnetic field, winding field lines around the solar interior like rubber bands being wound around a ball, building up magnetic stress that will eventually be released in spectacular violence. As sunspots are carried across the visible disk by the Sun's rotation, they transform from day to day. New spots emerge within the existing groups. Old spots decay and fade as their magnetic fields diffuse into the surrounding plasma. Spots that began as simple bipolar pairs, two spots of opposite magnetic polarity connected by looping magnetic field lines, can evolve into complex multipolar regions where field lines of different orientations are pressed together, storing enormous magnetic energy that can be released in sudden flares. The evolution of a large sunspot group over its weeks-long lifetime is a drama of planetary proportions, a slow-motion storm covering an area larger than Earth's surface, building toward potential eruption. And this evolution happens continuously, invisibly, whether humanity is watching or not. Right now, as you read these words, sunspots are emerging from the solar interior, growing from pores to mature spots, rotating across the visible disk, interacting with other magnetic regions, building magnetic stress, and eventually decaying back into the normal photosphere. Some will produce flares, sudden releases of magnetic energy that accelerate particles to near-light speed and emit radiation across the electromagnetic spectrum from radio waves to gamma rays. Some will trigger coronal mass ejections, billions of tons of plasma hurled into space at speeds of 1 to 2 million miles per hour. Some will affect Earth directly, producing geomagnetic storms that can disrupt power grids, damage satellites, and paint the polar skies with auroras visible as far south as Florida. The sun is not passive. It is not a simple source of warmth. It is a dynamic system of incomprehensible violence operating at scales your mind cannot contain, and every photon of light striking your skin right now is a messenger from that violence, a signal travelling 93 million miles to inform you that the monster is awake. But we have barely scratched the surface. We have spoken of the photosphere, the visible layer, the thin shell where light escapes. The photosphere is where the sun ends in terms of human vision, but it is not where the sun ends. Above the photosphere lie other layers, each hotter than the one below, each stranger than the one before. The temperature at the photosphere is roughly 10,000 degrees Fahrenheit. The temperature in the chromosphere, the layer immediately above the photosphere, rises to approximately 36,000 degrees Fahrenheit. And the temperature in the corona, the sun's outer atmosphere visible during total solar eclipses as a pearly white halo surrounding the darkened disk, exceeds 2 million degrees Fahrenheit. This is one of the most profound mysteries in solar physics, a paradox that troubled scientists for decades and is still not fully resolved. By all normal reasoning, temperature should decrease as you move away from a heat source. When you step away from a campfire, you feel cooler, not hotter. When you climb a mountain, the air grows colder the higher you ascend, even though you're moving closer to the sun. Yet the sun's atmosphere violates this intuition spectacularly. The photosphere, closest to the energy-generating core, is relatively cool. The corona, hundreds of thousands of miles above the photosphere, is hundreds of times hotter. Something is heating the corona from below, pumping energy into the sun's outer atmosphere through mechanisms that have only recently begun to be understood. The current best hypothesis involves magnetic waves and small-scale reconnection events called nanoflares. The sun's tangled magnetic field acts like a vast web of rubber bands being constantly stretched and twisted by plasma motions. When magnetic field lines of opposite polarity are forced together, they can reconnect, snapping into new configurations and releasing their stored magnetic energy as heat. If millions of tiny reconnection events occur throughout the corona every second, their combined heating could maintain the corona's extreme temperature. Space missions like the Parker Solar Probe, launched in 2018 and now approaching closer to the sun than any spacecraft in history, are gathering data that may finally solve this puzzle. But whether or not we understand why the corona is hot, we cannot deny what it does. This superheated atmosphere does not remain bound to the sun. It streams outward in all directions, thinning as it expands, creating a wind of charged particles that blows throughout the entire solar system. This is the solar wind, a constant outflow of protons, electrons, and heavier ions moving at speeds between 200 and 500 miles per second. The solar wind is not gentle. It carries enough momentum to push back the magnetic fields of planets, shape the tails of comets, and gradually erode the atmospheres of worlds that lack protective magnetic shields. The Earth is bathed in solar wind at all times. Roughly 400 kilometers per second, 1 million tons of solar material streams past our planet every single second. The only reason this wind does not strip away our atmosphere and sterilize the surface is our planet's magnetic field generated by convection in Earth's liquid iron outer core. This field creates a magnetic bubble around Earth called the magnetosphere, deflecting most of the solar wind around us like water flowing around a stone in a stream. Where the solar wind collides with Earth's magnetosphere, it creates a shock front, a boundary where the supersonic solar wind is suddenly decelerated to subsonic speeds. This bow shock sits roughly 90,000 kilometers sunward of Earth, invisible to human eyes but clearly visible to instruments that detect charged particles and magnetic fields. The solar wind is the monster's breath, blowing continuously through the void between worlds, touching every planet, every asteroid, every comet. It defines a region called the heliosphere, the sphere of the sun's influence, the domain where the solar wind dominates the interstellar medium. At the boundary of the heliosphere, roughly 100 astronomical units from the sun, 100 times the Earth-Sun distance, the solar wind finally becomes too weak to push back the thin gas that drifts between the stars. Here lies the heliopause, the edge of our stellar system in a plasma physics sense, the frontier where Voyager probes have finally passed after decades of flight. But even at this extreme distance, 9 billion miles from the Sun, the solar wind is still blowing, still carrying the Sun's influence outward, still testifying to the energy being released at a surface 300 light-minutes behind. The Sun is so large that you could place Earth at its centre and the Moon would still orbit inside its outer layers. The Sun is so massive that its gravity bends light and holds 8 planets in eternal attendance. The Sun is so powerful that its wind extends for billions of miles and defines the shape of our entire stellar neighbourhood. And yet, for all this scale and power and complexity, you have almost certainly spent your life thinking of it as a small yellow disk, a pleasant warmth on a summer afternoon, a simple and unremarkable thing. The monster deserves better. The creator deserves your attention. The star that made every atom of carbon in your body, every molecule of oxygen in your lungs, every trace of iron in your blood. This star deserves to be seen as it truly is. Not as the gentle disk your eyes perceive, but as the nuclear furnace your science reveals. Not as a passive backdrop to human affairs, but as the central engine driving all life, all weather, all energy flows in our corner of the galaxy. What lies ahead will take us deeper into this engine. We will descend below the photosphere into regions where pressure would crush any spacecraft, where photons take thousands of years to escape, where matter exists in states unknown on Earth. We will watch flares explode with the energy of billions of nuclear weapons and coronal mass ejections hurl continents of plasma toward our fragile world. We will trace the history of our understanding, from ancient sun gods to modern space probes skimming the corona at speeds that would circle Earth in minutes. But the journey there will fundamentally alter how you think about scale, about violence, about the delicate balance that allows you to exist at all. The photosphere, that 5,778-degree surface we have already explored, is merely the visible skin of something far more vast and far more strange. It is where our eyes can reach, but not where the Sun's story truly unfolds. To understand the monster, we must go deeper, through the surface, past the convection zone where plasma churns like water in a boiling pot, down into regions where the physics becomes increasingly alien and the conditions increasingly impossible. Directly beneath the photosphere lies the convection zone, a region approximately 200,000 kilometers deep, where energy moves primarily through the bulk motion of plasma. Hot plasma rises toward the surface, cools as it radiates energy into space, becomes denser, and sinks back down to be reheated. This is the same process you observe when heating soup on a stove, the convection pattern, where hot material rises and cool material falls. But the scale defies domestic comparison. Each convection cell at the solar surface, the granules we discussed earlier, represents only the uppermost expression of convection columns that may extend tens of thousands of kilometers downward. Deeper still, supergranulation cells span 30,000 kilometers across, and beneath these, giant cells may exist that stretch across significant fractions of the solar radius, though these remain difficult to detect directly. The plasma in the convection zone moves at speeds that vary with depth. Near the photosphere, convective velocities reach roughly 1 to 2 kilometers per second. Deeper in the convection zone, the speeds may increase to several kilometers per second. This motion is not orderly. It is turbulent, chaotic, constantly churning. If you could somehow illuminate the convection zone and watch it from outside, you would see not the steady flow of a river but the violent roiling of a waterfall, plasma tumbling over itself in 3 dimensions, magnetic fields stretched and twisted and amplified by the motion. This turbulent motion is where the Sun's magnetic field is generated. The dynamo process, as it is known, converts the kinetic energy of moving plasma into magnetic energy. The Sun is not a permanent magnet like a bar of iron. Its magnetic field is constantly being generated, destroyed and regenerated by the motion of electrically conducting plasma through the convection zone. This is why the solar magnetic field is so complex and variable, why sunspots come and go, why the Sun's activity waxes and wanes on an 11-year cycle. The magnetic field is not a static structure but a dynamic one, as restless and turbulent as the plasma that creates it. Below the convection zone, At approximately 70% of the solar radius measured from the centre lies a boundary layer called the tachocline. Here, the physics changes dramatically. Above this boundary, plasma rotates at different speeds at different latitudes, the Sun's differential rotation, where equatorial regions complete a rotation in about 25 days, while polar regions take roughly 35 days. Below the tachocline, in the radiative zone, the Sun rotates as a rigid body, all parts turning at the same rate. The tachocline is a thin layer of extreme shear, where the differentially rotating convection zone meets the rigidly rotating radiative zone. This shear is now believed to be crucial for generating and amplifying the Sun's magnetic field. The tachocline acts like a magnetic amplifier, stretching and intensifying field lines as they are dragged through this zone of velocity difference. The radiative zone extends from the tachocline down to approximately 25% of the solar radius. This region accounts for roughly 32% of the Sun's volume but contains 48% of its mass. Here, energy no longer moves by convection. The plasma is so dense, so opaque to electromagnetic radiation, that photons cannot travel far before being absorbed. Yet convection cannot occur because the temperature gradient is not steep enough to drive bulk plasma motion. Instead, energy moves by radiation. Photons are emitted, absorbed, re-emitted in random directions, absorbed again, re-emitted again, in a process that has been compared to a drunk stumbling through a crowd. The implications of this radiative transfer are profound. A photon generated in the solar core does not stream directly outward to escape at the photosphere. It bounces and bounces and bounces again. The average distance a photon travels before being absorbed, its mean free path, is less than 1 centimetre in the dense plasma of the radiative zone. To travel the 500,000 kilometres from the edge of the core to the bottom of the convection zone requires an almost incomprehensible number of absorption and re-emission events. The time this takes has been calculated by physicists using random walk models. If you take a step forward or backward at random, how long does it take to travel a certain distance? The answer depends on step size and total distance. For photons in the radiative zone, with their sub-centimetre mean free path, the calculation yields a stunning result. The journey from core to convection zone takes somewhere between 10,000 and 170,000 years, depending on assumptions about plasma opacity and the exact nature of the random walk. The most commonly cited figure is approximately 170,000 years, though some models suggest it may be as short as 17,000 years. Consider what this means. The sunlight warming your face right now began its outward journey when mammoths still walked the earth, or perhaps when Neanderthals still lived alongside our ancestors, or perhaps when modern humans were first developing language. The photon you see was created during an ice age, or several ice ages ago, and has spent the entire span of human civilization bouncing through the solar interior, slowly diffusing outward, finally escaping from the photosphere 8 minutes ago to reach your eyes at this instant. The light that powers your biology is older than recorded history. It is a message from the deep past, finally delivered after geological ages of random wandering through plasma so dense it makes steel look like vacuum. But even the radiative zone is not where the sun's energy originates. For that, we must descend to the core, the innermost 15 to 25% of the solar radius. Here, in a volume roughly the size of Jupiter, conditions reach their most extreme. The temperature at the solar centre is approximately 15 million degrees Celsius, roughly 27 million degrees Fahrenheit. The pressure is approximately 250 billion atmospheres. The density is 150 grams per cubic centimetre, roughly 13 times the density of lead, though the matter remains gaseous because the extreme temperature keeps atoms stripped of their electrons. In these conditions, hydrogen nuclei, protons, move so fast that they can overcome their natural electrical repulsion and occasionally fuse together. The process is not simple. 2 protons cannot simply stick together. The resulting nucleus would be helium-2, which is unstable and flies apart almost instantly. Instead, solar fusion proceeds through a series of reactions called the proton-proton chain. In the first step, 2 protons collide with such violence that one of them transforms into a neutron through the weak nuclear force, releasing a positron and a neutrino. The resulting deuterium nucleus, 1 proton and 1 neutron, is stable. In the second step, another proton strikes the deuterium nucleus, forming helium-3 and releasing a gamma-ray photon. In the third step, two helium-3 nuclei collide to form helium-4 plus two protons, which are recycled back into the fusion process. The net result, 4 hydrogen nuclei become one helium nucleus, 2 positrons, 2 neutrinos, and energy. The energy appears because the helium nucleus has slightly less mass than the 4 hydrogen nuclei that created it. This mass difference, about 0.7% of the original mass, is converted to energy according to Einstein's equation. For every kilogram of hydrogen fused into helium, approximately 7 grams of mass disappear, converted into roughly 600 trillion joules of energy. The Sun converts approximately 600 million tons of hydrogen into helium every second, with 4 million tons of mass being converted directly into energy. 4 million tons per second. This is the rate at which the Sun is literally evaporating, converting its own substance into energy and radiating it into space. Over its 4.6 billion year lifetime, the Sun has converted approximately 100 Earth masses of matter into pure energy. This sounds catastrophic until you remember the Sun's total mass, 2,000 billion kilograms. 100 Earth masses is roughly 0.03% of the Sun's original mass. The monster can afford to be profligate because the monster is unimaginably vast. The neutrinos produced in fusion reactions are particularly interesting because they barely interact with matter at all. While photons take 100,000 years or more to diffuse outward, neutrinos escape from the core at essentially the speed of light, reaching Earth approximately 8 minutes after their creation. Every second, roughly 65 billion solar neutrinos pass through every square centimetre of your body. Right now, as you read this, trillions of neutrinos are streaming through your eyes, your brain, your heart, having been created in the solar core 8 minutes ago. You cannot feel them. They pass through the entire planet as if it were not there. But their detection by enormous underground experiments has confirmed that solar fusion proceeds exactly as theory predicts. The Sun's core is not a mystery. We have measured it directly, using particles that nothing can stop. The energy released in fusion appears initially as gamma rays, photons of extreme energy created in nuclear reactions. These gamma rays have wavelengths measured in picometers and energies measured in mega-electron volts. By the time these photons reach the photosphere, after their 100,000-year journey of absorption and re-emission, they have been transformed. Each high-energy gamma ray has been absorbed, its energy distributed among many lower-energy photons. The gamma rays created in fusion become X-rays, then ultraviolet light, then visible light, then infrared. The spectrum of sunlight you see, the rainbow of colours from violet to red, represents the final form of energy that began as gamma radiation in the core. The transformation is so complete that no trace of the original gamma rays remains in sunlight. The fusion fire has been tamed, its violence filtered by 500,000 kilometres of plasma, until it emerges as the gentle warmth of a spring morning. But the Sun's interior is only half the story. Above the photosphere, the monster extends outward into what initially seems like mere atmosphere, but reveals itself as something far more dynamic and dangerous. The chromosphere, which we touched upon briefly, rises from the photosphere's edge to approximately 2,000 kilometers altitude. This region gets its name from the Greek word for colour, because it appears as a thin red layer during total solar eclipses, visible for just seconds as the moon covers and then uncovers the solar disk. The red colour comes from hydrogen atoms emitting light at a specific wavelength, 656.3 nanometers, known as hydrogen alpha, as their electrons fall from the third to the second energy level. The chromosphere presents a paradox that troubled solar physicists for decades. As you rise from the photosphere into the chromosphere, the temperature initially continues to drop, reaching a minimum of approximately 4,400 degrees Celsius, about 500 kilometers above the visible surface. This makes intuitive sense. You are moving away from the hot solar interior, so things should get cooler, but then the temperature begins to rise again. By the top of the chromosphere, temperatures have climbed back to roughly 20,000 degrees. This is deeply strange. It is as if you walked away from a campfire and the air got hotter the further you walked. The explanation lies in the magnetic field and the mechanical energy it transports. Sound waves, magnetic waves, and shock waves generated in the convection zone propagate upward through the chromosphere. As these waves travel into less dense plasma, their energy becomes concentrated. When the waves steepen into shocks and dissipate, they deposit their energy as heat. The chromosphere is being heated not by radiation from below, but by mechanical energy transported from below by waves travelling along magnetic field lines. The chromosphere is also where we see some of the Sun's most visually dramatic structures. Spicules, jets of plasma that shoot upward from the chromosphere at speeds of 20 to 30 kilometers per second, rise for 5 to 10,000 kilometers before falling back or dissipating. At any given moment, roughly 300,000 spicules are active on the Sun. They last only 5 to 10 minutes each, but collectively transport significant mass and energy into the outer atmosphere. In time-lapse images, the chromosphere looks like a forest of flames, plasma fountains constantly rising and falling, a landscape of perpetual explosive activity that would dwarf any earthly catastrophe. Above the chromosphere, a thin and variable transition region marks the boundary to the corona. Across this region, which may be only a few hundred kilometers thick, the temperature rises from 20,000 degrees to over 1 million degrees. This increase, a factor of 50 or more, occurs over a distance comparable to the length of a small country. The transition region is not a smooth boundary, but a highly structured dynamic interface where magnetic field lines concentrate the heating and create dramatic temperature contrasts over small distances. And then comes the corona, the Sun's outer atmosphere, where temperatures reach 1 to 3 million degrees Celsius, and the density drops to levels comparable to the vacuum in a laboratory on Earth. The corona is the part of the Sun visible during total eclipses, the ethereal white glow surrounding the black disk of the Moon, streamers of light extending for several solar radii into space. Renaissance astronomers who witnessed total eclipses recorded this glow but had no framework for understanding it. They might have thought it an optical illusion, or an atmospheric effect, or the halo of some divine presence. The truth is stranger than any of these interpretations. The corona is hotter than the surface beneath it. This violates what seems like common sense. If you have a source of heat, temperatures should decrease as you move away from it. The surface of a stove is hotter than the air above the stove. The filament of a light bulb is hotter than the glass envelope surrounding it. Yet the Sun's corona is hundreds of times hotter than the photosphere, despite being further from the fusion reactions in the core. This coronal heating problem, as it is known, remained one of the great mysteries of solar physics for decades after the corona's temperature was first measured spectroscopically in the 1940s. The solution, still not fully understood in all its details, involves the same magnetic mechanisms that heat the chromosphere, amplified to even greater effect. Magnetic field lines threading through the corona are constantly being twisted, braided and stressed by convective motions at the photosphere. When these stressed field lines reconnect, when oppositely directed magnetic fields are forced together and reconfigure, enormous amounts of energy are released in very small volumes. This magnetic reconnection can heat plasma to millions of degrees almost instantaneously. Some researchers believe the corona is heated by countless tiny magnetic reconnection events called nanoflares, individually too small to detect, but collectively releasing enough energy to maintain coronal temperatures. Others emphasize the role of waves, Alphin waves travelling along magnetic field lines, carrying energy from the convection zone and depositing it in the corona through complex damping mechanisms. The Parker Solar Probe, launched in 2018 and currently making closer approaches to the Sun than any previous spacecraft, is gathering data that may finally resolve this decades-old question. The corona is not uniform. It has structure determined entirely by the Sun's magnetic field. Where magnetic field lines arch from one point on the photosphere to another, forming closed loops, the corona is bright and hot. These coronal loops can extend hundreds of thousands of kilometers into space, plasma trapped on magnetic field lines like beads on a wire, glowing at temperatures of several million degrees. Where magnetic field lines extend straight outward without returning to the surface, open field lines leading into interplanetary space, the corona is dimmer and cooler, forming structures called coronal holes. These coronal holes are the source of the fast solar wind, plasma escaping along open field lines at speeds of 700 to 800 kilometers per second. The magnetic structuring of the corona creates a landscape of staggering complexity. Satellite images of the Sun in extreme ultraviolet light, which reveals plasma at coronal temperatures, show a surface covered with loops, arches, plumes, and tunnels of glowing gas. Different temperatures show different structures. Cooler plasma near 1 million degrees reveals certain features, while hotter plasma at 3 to 5 million degrees reveals others. The corona is not a static atmosphere, but a dynamic, constantly changing environment shaped by magnetic forces that would be impossible on any world without a stellar engine driving them. It is in this magnetically dominated corona that the Sun's most violent events occur. Solar flares, the sudden brightening of small regions on the solar surface, release energy equivalent to billions of hydrogen bombs detonating simultaneously. The energy comes from magnetic reconnection, the sudden reconfiguration of stressed magnetic field lines, releasing energy that has been stored in the magnetic field over days or weeks of gradual build-up. A large solar flare can release 10 to the power of 25 joules of energy in a matter of minutes, equivalent to the total energy output of human civilization over several 100,000 years. The radiation from a solar flare spans the electromagnetic spectrum. X-rays and extreme ultraviolet light reach Earth in approximately 8 minutes, travelling at the speed of light. When this radiation hits Earth's upper atmosphere, it ionizes atoms, temporarily increasing the electron density in the ionosphere and disrupting radio communications. High-frequency radio signals that normally bounce off the ionosphere may instead be absorbed, causing radio blackouts that can affect aviation communications and other critical systems. The March 1989 solar storm that knocked out the Hydro-Quebec power grid was triggered by a series of flares that sent energetic particles streaming toward Earth. But flares are only the beginning. Often accompanying large flares, though sometimes occurring independently, are coronal mass ejections, or CMEs. These are eruptions not of radiation but of matter. Billions of tons of coronal plasma carrying embedded magnetic fields are blasted outward from the Sun at speeds ranging from hundreds to thousands of kilometers per second. A fast coronal mass ejection can reach Earth in as little as 15 to 18 hours. A slow one may take several days, but when one arrives, it can compress and distort Earth's magnetosphere, trigger geomagnetic storms, and create auroras visible far from the polar regions. The energy in a large coronal mass ejection is staggering. A single CME may carry 10 to the power of 25 joules of kinetic energy, comparable to a major solar flare. The mass ejected, typically 1 to 10 billion tons of plasma, represents a significant chunk of the corona being hurled into space. If you could somehow see a coronal mass ejection approaching Earth, it would appear as an expanding bubble of magnetized plasma, a wall of charged particles spanning millions of kilometers, bearing down at 1,000,000 miles per hour. The mechanism driving coronal mass ejections involves the same magnetic dynamics that cause flares, but on a larger scale. Twisted magnetic field lines, stressed beyond their stability limits, can erupt outward, carrying trapped plasma with them. In many cases, the eruption begins with a prominence, a dense structure of relatively cool plasma suspended in the corona by magnetic fields, being destabilized and ejected. Prominences can hang in the corona for days or weeks, dense clouds of gas at merely 10,000 degrees floating in an ocean of million-degree plasma, held up against gravity solely by the magnetic field. When the supporting magnetic structure fails, the prominence erupts, and the coronal mass ejection is born. The Sun experiences roughly 1 to 3 coronal mass ejections per day during the active phase of its 11-year cycle, and perhaps one every few days during solar minimum. Not all are directed toward Earth. The Sun ejects material in all directions, and only those CMEs aimed at our planet pose any concern. But over the course of a solar cycle, Earth is struck by dozens of significant coronal mass ejections, each one a reminder that we live within the extended atmosphere of a star. The consequences of this bombardment range from beautiful to catastrophic. At the benign end, geomagnetic storms triggered by CMEs energize particles in Earth's magnetosphere, which then spiral down along magnetic field lines and collide with atmospheric atoms at high latitudes. The resulting auroras, northern and southern lights, create ribbons and curtains of green, red and purple light dancing across the night sky. People travel thousands of miles to witness these displays, not realizing they are seeing the aftermath of solar violence, the trace signature of a monster breathing. At the catastrophic end lies something far more sobering. The same mechanisms that paint the polar skies with ethereal light can, under the right conditions, bring modern civilization to its knees. This is not speculation. It has happened before, and the historical record carries a warning that grows more urgent with each passing year. On the morning of September 1st, 1859, a 33-year-old English astronomer named Richard Carrington was conducting his daily observations of sunspots from his private observatory in Redhill, Surrey. He had been meticulously tracking and sketching the positions of sunspot groups for years, contributing to the growing understanding of solar activity. At approximately 11:18 a.m. local time, something unprecedented occurred. While observing a particularly large and complex sunspot group, Carrington witnessed two intensely bright patches of white light suddenly appear within the sunspot region. The flare was so brilliant that it overwhelmed the filtered image of the sun itself. Carrington watched, astonished, as the brilliant patches travelled across the sunspot group over approximately 5 minutes before fading. He later wrote that the phenomenon was so unexpected that he initially doubted his own eyes. Independently, another English astronomer named Richard Hodgson, observing from a different location, witnessed the same event. Their simultaneous observations provided crucial confirmation. What they had seen was the first recorded observation of a solar flare, and it remains the most powerful solar storm ever documented in the era of scientific instrumentation. Less than 18 hours later, Earth's magnetic field went haywire. The coronal mass ejection triggered by the Carrington event, as it came to be known, reached Earth with extraordinary speed. Typical CMEs take 2 to 4 days to make the journey. This one arrived in approximately 17.5 hours, implying a speed of over 2,000 kilometers per second. When it struck Earth's magnetosphere, the consequences were immediate and dramatic. Telegraph systems across North America and Europe failed catastrophically. Operators reported receiving electrical shocks from their equipment. Telegraph paper spontaneously caught fire. Perhaps most remarkably, some telegraph lines continued to operate even after operators disconnected their batteries entirely. The current induced by the geomagnetic storm was sufficient to power the systems without any external electricity. Auroras were seen as far south as the Caribbean, Hawaii, and northern Colombia. Residents of the northeastern United States reportedly could read newspapers by the light of the aurora alone. The sky glowed red across much of the world, and confused observers in many regions thought dawn was breaking in the middle of the night. The Carrington event occurred in 1859, when the most sophisticated electrical technology was the telegraph. The damage, while disruptive, was manageable. The world continued to turn. But consider what has happened to human civilization in the century and a half since. We have wired the planet with a web of electrical infrastructure so vast and interconnected that it defies comprehension. High-voltage transmission lines snake across continents, carrying power from generating stations to cities hundreds or thousands of kilometers away. Transformers step voltage up and down at every junction. Satellites orbit overhead by the thousands, providing navigation, communication, weather monitoring, and military surveillance. Undersea cables carry the bulk of internet traffic between continents. Financial systems process trillions of dollars in transactions every day, dependent on networks that span the globe. Aviation relies on GPS for navigation and radio for communication. Modern agriculture, water treatment, medical facilities, and food distribution systems all depend on continuous electrical power. Now imagine the Carrington event striking today. Studies by the National Academy of Sciences, NASA, and Lloyd's of London have attempted to model the consequences. The conclusions are sobering. A severe geomagnetic storm, on the scale of the Carrington event or greater, would induce electrical currents in long-distance power lines and transformers that could cause catastrophic damage to electrical grids across multiple continents simultaneously. High-voltage transformers, many of which are custom-built and take 18 months to 2 years to manufacture, could be destroyed in large numbers. Without these transformers, vast regions could be without power for months or even years. The cascading failures would be difficult to contain. A 2008 report by the National Academy of Sciences estimated that a severe geomagnetic storm could cause economic damage exceeding $2 trillion in the first year alone, with full recovery taking 4 to 10 years. Some estimates place the figure considerably higher. The damage would not be limited to power grids. Satellites are particularly vulnerable to the enhanced radiation and charged particle flux during major solar storms. The same energetic particles that create auroras can penetrate satellite electronics, causing malfunctions, data corruption, and permanent damage. During severe storms, satellites have been known to tumble out of control, lose communication capability, or fail entirely. The Starlink constellation operated by SpaceX lost dozens of satellites in a single, moderate geomagnetic storm in February 2022, when enhanced atmospheric drag caused by heating in the upper atmosphere led to re-entry and destruction. A Carrington-class event would affect satellites in all orbital regimes, potentially crippling GPS, telecommunications, and weather forecasting for extended periods. Ground-based communications would fare little better. High-frequency radio blackouts, lasting hours to days, would disrupt aviation communications and navigation. Airlines flying polar routes, which rely on HF radio for communication in regions beyond satellite coverage, would be forced to reroute, causing delays and economic disruption. Emergency services dependent on radio communication could find themselves unable to coordinate. Pipeline systems carrying oil and gas across continents, which use cathodic protection systems to prevent corrosion, could suffer accelerated corrosion damage. Even the cables carrying internet traffic across ocean floors are vulnerable. The repeaters that boost signals along undersea cables are designed to operate within certain electrical tolerances, and geomagnetically induced currents could damage or destroy them. The terrifying truth is that we do not know precisely when the next Carrington-class event will occur, only that it will occur. The Sun has produced such events before, and it will produce them again. Statistical analysis of ice cores, which preserve chemical signatures of past solar events, suggests that events of similar or greater magnitude occur roughly once or twice per century. The September 1859 event was not unique. In July 2012, a coronal mass ejection of comparable intensity to the Carrington event erupted from the Sun and crossed Earth's orbital path. Had the eruption occurred 1 week earlier, Earth would have been directly in the line of fire. We missed a direct hit by approximately 9 days of orbital motion. Daniel Baker, a space weather expert at the University of Colorado, later remarked that if the 2012 CME had struck Earth, we would still be picking up the pieces. We were lucky. We may not be lucky again. The recognition of this vulnerability has driven significant investment in space weather forecasting and monitoring. The Deep Space Climate Observatory, or DSKOVR, launched in 2015 and positioned at the first Lagrange point between Earth and Sun, provides approximately 15 to 60 minutes of warning before a CME arrival. The Solar and Heliospheric Observatory, SOHO, launched in 1995, monitors solar activity continuously, as do a network of ground-based solar observatories and orbiting instruments. Scientists have developed increasingly sophisticated models for predicting which solar active regions are most likely to produce major eruptions, and for forecasting the trajectory and intensity of coronal mass ejections once they occur. But prediction remains imperfect. The magnetic structure of a CME, particularly the orientation of its embedded magnetic field, which largely determines how severely it will affect Earth, often cannot be determined until the CME has nearly arrived. The warning time for truly catastrophic storms may be measured in hours, not days. This is what it means to live beside a star. The light that sustains us arrives wrapped in invisible peril. The same energy that drives photosynthesis and warms the atmosphere can, in concentrated bursts, threaten the technological civilization we have built. We have become dependent on systems that the Sun can disrupt with a single exhalation, and the Sun, indifferent to our dependencies, continues its ancient rhythms, coiling and releasing magnetic tension in cycles we are only beginning to understand. But solar flares and coronal mass ejections, however dramatic, represent only the Sun's everyday violence. There exists a deeper category of solar phenomena, events so rare and so powerful that they strain our understanding of what our star is capable of. Events that make the Carrington storm look modest by comparison. Events whose occurrence we have only recently discovered through the forensic analysis of ancient records written not on paper, but in the very atoms of our planet. In the year 2012, a team of researchers led by Fusa Miyake at Nagoya University in Japan published a remarkable discovery. By analysing the concentration of carbon-14 in the annual growth rings of ancient Japanese cedar trees, they detected an anomaly. In the year 774 CE, the amount of radioactive carbon-14 produced in Earth's atmosphere spiked dramatically, increasing by approximately 1.2% in a single year. This may sound insignificant. It is not. Carbon-14 is produced when cosmic rays strike nitrogen atoms in the upper atmosphere. The rate of production is normally quite stable, varying only slightly with the 11-year solar cycle. An increase of 1.2% in a single year implied an influx of cosmic rays or high-energy particles far beyond anything observed in the modern era. The cause was not immediately apparent. Researchers considered various possibilities. A nearby supernova, a gamma ray burst from a distant cosmic explosion, a massive solar energetic particle event. Subsequent investigations, including measurements of beryllium-10 in ice cores from Antarctica and Greenland, another isotope produced by cosmic ray bombardment, confirmed the anomaly and pointed increasingly toward a solar origin. The event of 774 CE, now known as the Miyake event, appears to have been a solar proton event of staggering intensity, somewhere between 10 and 100 times more powerful than any recorded in modern times. Some estimates suggest the particle fluence exceeded the Carrington event by more than an order of magnitude. What happened on Earth in 774 CE when this torrent of particles arrived? We do not know with certainty. Written records from that era are sparse, and the chroniclers of the time would not have understood the connection between unusual celestial phenomena and the invisible flux of particles bombarding their atmosphere. Some researchers have pointed to references in the Anglo-Saxon Chronicle to a red crucifix appearing in the sky after sunset in the year 774, possibly an aurora seen at unusually low latitudes, but such identifications remain speculative. What we do know is that additional Miyake events have been identified in the tree ring and ice core records. Another major event occurred in 993 CE, roughly two-thirds the intensity of the 774 event. More have been identified in the deeper past, in 7176 BCE, in 5259 BCE, and at other points extending back thousands of years. The frequency appears to be roughly one such event every few centuries to a millennium. They are rare, but they occur, and when they occur they deposit vastly more energy into Earth's atmosphere than any solar storm observed since the beginning of the space age. The implications are profound. If a Miyake-class event occurred today, the consequences would dwarf those of a Carrington-class storm. Satellites would be destroyed in massive numbers. Astronauts aboard the International Space Station or any future lunar or Martian missions would receive potentially lethal radiation doses unless adequately shielded. Aircraft flying at high altitudes, particularly near the poles, would expose passengers and crew to significantly elevated radiation. The geomagnetically induced currents in power grids would reach intensities for which no infrastructure has been designed. And unlike Carrington-class events, which provide at least some warning through solar observation, the highest energy solar proton events travel at near-light speeds and can arrive at Earth within tens of minutes of the triggering flare, faster than any practical warning system could respond. We do not know what triggers these extreme events. They appear to be rare manifestations of the same magnetic reconnection processes that produce ordinary flares, but scaled up to extraordinary intensity. Some researchers speculate that they may require particularly complex magnetic field configurations, perhaps involving multiple active regions interacting simultaneously. Others suggest that the relationship between flare intensity and particle emission may be nonlinear, with certain events crossing thresholds that lead to runaway particle acceleration. The honest answer is that we do not yet understand the Sun well enough to predict when such an event might occur. This uncertainty weighs heavily on the minds of those who study space weather. We have built a civilization exquisitely vulnerable to a type of event that our star produces with some regularity on geological timescales. The last Miyake event occurred over 1,000 years ago. We have no guarantee that the next one will not occur tomorrow, and yet, for all the violence the Sun visits upon its domain, there is a deeper irony embedded in our relationship with it. The same magnetic activity that threatens our civilization is intimately connected to the processes that made complex life possible in the first place. The Sun's magnetic field extends outward through the solar system, carried by the solar wind, forming a vast bubble called the heliosphere that encompasses all the planets and extends perhaps twice the distance from the Sun to Pluto. This heliosphere acts as a shield, deflecting the majority of galactic cosmic rays, high-energy particles from distant supernovae and other cosmic accelerators that would otherwise bombard the inner solar system with far greater intensity. Without the Sun's magnetic activity, without the solar wind that carries that magnetism outward, Earth would be subject to a significantly higher cosmic ray flux. The implications for the evolution of life, for the stability of DNA, for the viability of complex organisms on Earth's surface remain a subject of active research. But it is entirely plausible that the same solar activity we fear also provided conditions necessary for our existence. The Sun, then, is not merely a danger to be guarded against. It is a complex partner in our existence, providing light and warmth with one hand while occasionally lashing out with the other. Understanding this relationship, quantifying the risks, developing the forecasting capabilities, building the resilience into our infrastructure, has become one of the quiet imperatives of the 21st century. Space weather research, once a niche academic pursuit, has moved steadily toward the centre of national security and economic planning discussions. Governments increasingly recognise that the next major solar storm is not a matter of if, but when, and that the costs of unpreparedness could be measured in human lives and decades of recovery. But there is something more than practical concern that emerges from contemplating the Sun's violence. There is a philosophical shift, a realignment of perspective that comes from truly grasping our position in the cosmos. We are not separate from the Sun. We are not observers watching from a safe distance. We live within its atmosphere, bathed in its radiation, subject to its moods. Every sunrise reminds us of the connection, though we seldom acknowledge its deeper implications. The distance between us, one astronomical unit, 150 million kilometres, provides an illusion of safety. But that distance is nothing against the scale of what the Sun actually is. The light that falls upon your face in the morning began as gamma radiation in the core, absorbed and re-emitted countless times over tens of thousands of years before finally escaping into space and crossing the void to your window in 8 minutes. That light connects you directly to the fusion reactions at the heart of a star. Every cell in your body, every atom you're composed of was forged either in the Big Bang or in the death throes of stars that predated our Sun. You are made of stellar material, living on a rocky sphere orbiting stellar material, utterly dependent on stellar processes for your continued existence. The Sun does not care about you. It does not know you exist. It is a ball of plasma governed by physics, nothing more. And yet, in a universe that has no obligation to produce consciousness or meaning or beauty, here you are, thinking about the Sun, understanding the Sun, marvelling at the Sun. This reciprocity, this unlikely capacity of matter to contemplate itself, emerges from precisely the same processes that sometimes threaten to destroy us. The energy that could collapse our power grids is the same energy that powered the evolution of brains capable of understanding power grids. We stand at a peculiar moment in our relationship with the Sun. For the first time in the 4.5 billion years that Earth has orbited this star, a species has arisen that can observe the Sun's behaviour, predict its outbursts to some degree, and take action to protect itself. For the first time, the Sun's tantrums need not be simply endured. They can be anticipated and mitigated. This is a profound development, a break from the passivity that characterized all previous life on this planet. We are no longer entirely at the mercy of our star, but we are not yet safe. The gap between our understanding and the Sun's complexity remains vast. The predictive models improve year by year, but major eruptions can still surprise us. The warning systems provide precious hours of advance notice, but the infrastructure to respond, to take power grids offline in time, to shelter satellites behind Earth's shadow, to protect astronauts from particle storms, remains incomplete. We have recognised the danger without yet fully addressing it, and beneath all the practical considerations lies the simple, irreducible fact of our situation. We orbit a thermonuclear explosion. We have done so for billions of years. We will continue to do so for billions more, assuming we survive our own folly and the occasional violence of our star. That explosion gives us everything we have, and periodically reminds us that it could take it all away. This is not a comfortable position. It is not meant to be. The universe did not design itself for our comfort, but it is a position that rewards understanding. The more clearly we see the Sun for what it actually is, not the small yellow disk of casual perception, but the colossal fusion reactor dominating our existence, the better equipped we become to navigate our relationship with it. The Sun has more surprises in store for us. Its behaviour over the coming decades and centuries will shape the future of human civilization in ways we can only partially anticipate. And the story does not end with violence. Beyond the flares and the storms, beyond the magnetic chaos and the billion-ton plasma clouds, there is a longer arc to the sun's existence, a trajectory that stretches billions of years into the future and holds implications for every living thing on Earth. The sun you see today is not the sun that will exist tomorrow. This is true in the trivial sense that the sun changes moment by moment, its surface a perpetual storm of convection and magnetic activity. But it is also true in a deeper sense, one that operates on timescales so vast they strain the capacity of human minds to meaningfully grasp. The sun is aging. It has been aging since the moment of its birth 4.5 billion years ago, and it will continue to age until the moment of its death, approximately 5 billion years from now. And in that aging lies a story that encompasses not merely the fate of our star, but the ultimate destiny of every world that orbits it. To understand what the sun will become, you must first understand what it currently is in a more fundamental way than we have yet explored. The sun is a main sequence star, a classification that sounds technical but describes something elegantly simple. It is a star in the stable middle phase of its existence, fusing hydrogen into helium in its core at a rate that has remained roughly constant for billions of years. This stability is not accidental. It emerges from a precise balance between two opposing forces: the crushing inward pressure of gravity trying to collapse the sun under its own weight, and the outward pressure of the energy released by fusion reactions pushing back against that collapse. For as long as the sun has sufficient hydrogen fuel in its core to sustain fusion at the necessary rate, this balance holds. The sun neither collapses nor expands. It simply burns, steady and reliable, a cosmic furnace maintaining its temperature within remarkably narrow bounds. But the fuel is finite. This is the inescapable arithmetic of stellar existence. Every second, the sun converts approximately 600 million tons of hydrogen into helium. This sounds like an unsustainable rate of consumption, and in the longest view it is. But the sun's hydrogen reserves are so vast, roughly 70% of its total mass at birth, that even this prodigious consumption can continue for billions of years. The sun has burned through approximately half of its core hydrogen supply. It has roughly 5 billion years of main sequence life remaining, give or take a few 100 million years depending on the precise models one consults. 5 billion years. The number is so large it becomes almost meaningless. 5 billion years ago, Earth did not exist. The solar system itself was still a swirling disk of gas and dust surrounding the young sun. Life had not yet emerged anywhere in our cosmic neighbourhood. Multicellular organisms would not appear for another 3 billion years. Dinosaurs were still 4.5 billion years in the future. Human beings, with their telescopes and their mathematics, and their capacity to worry about distant futures, were so far from existence that the very concept of them would have been incomprehensible to any observer present at the sun's birth, had any observer been possible in that chaotic, molten epoch. And yet, 5 billion years will pass. Time moves forward with absolute indifference to our difficulty in conceiving it. The sun will exhaust its core hydrogen, and when it does, everything will change. The transformation will not happen suddenly. Stars do not switch off like light bulbs. Instead, the sun will undergo a gradual metamorphosis that unfolds over hundreds of millions of years. A geological eye blink in cosmic terms, but still a span of time longer than any species has ever existed on Earth. As the core hydrogen depletes, the fusion reactions that have sustained the sun for so long will begin to falter. The outward pressure they generate will decrease, and for the first time since its birth, gravity will gain the upper hand. The core will begin to contract. This contraction will do something counterintuitive. It will heat the core rather than cool it. As the core compresses under its own gravity, gravitational potential energy converts to thermal energy, and the temperature rises. This heating will extend the sun's life somewhat, as a hotter core can fuse hydrogen more efficiently. But it will also begin to change the sun's structure in fundamental ways. The increased temperature will cause hydrogen fusion to spread outward, from the depleted core into a shell surrounding it, a ring of nuclear fire burning through fresh fuel that the core itself can no longer access. This shell burning will have profound consequences. The energy released by the hydrogen shell will be dumped into the layers above it, causing them to expand outward. The sun will begin to swell. At first, the expansion will be gradual, barely noticeable on human timescales, even if humans still existed to notice. But as millions of years pass, the expansion will accelerate. The sun's outer layers will push outward, cooling as they expand, and the star's colour will shift from yellow-white toward orange, then toward red. The sun will become what astronomers call a subgiant star, larger and cooler than its current state, though still recognisable as the same celestial object. But this is merely a transitional phase. The true transformation lies ahead. As the core continues to contract and heat, it will reach a temperature of approximately 100 million degrees Celsius, 10 times hotter than the current core temperature. At this threshold, something remarkable becomes possible. The accumulated helium in the core, the ash product of billions of years of hydrogen fusion, will itself become fuel. At 100 million degrees, helium nuclei possess enough kinetic energy to overcome their mutual electrical repulsion and fuse together, forming heavier elements. 3 helium nuclei combine to form a single carbon nucleus, in a process called the triple alpha reaction. The sun will ignite a new nuclear furnace, one that burns a different fuel at vastly higher temperatures. This helium ignition will occur with explosive violence. In stars of the sun's mass, the core at this point is supported not by normal gas pressure, but by a quantum mechanical effect called electron degeneracy pressure. This pressure does not respond to temperature increases in the normal way. When helium fusion ignites, the sudden release of energy does not cause the core to expand and cool, the usual feedback mechanism that keeps fusion reactions stable. Instead, the temperature spikes dramatically, causing fusion to proceed even faster, releasing more energy, raising the temperature further. This runaway process, called the helium flash, releases an enormous burst of energy in a matter of minutes, roughly as much energy as the entire Milky Way galaxy produces in the same time span. And yet, you would see nothing from Earth. If Earth still exists at this point, and if any observer remains upon it, they would notice no change in the sun's appearance at the moment of the helium flash. The energy is released deep in the core, and it is absorbed by the overlying layers before it can reach the surface. The flash is hidden, a secret catastrophe buried beneath a trillion tons of stellar material. The sun keeps its violence private, at least this particular violence. The consequences will emerge later, over the following millions of years, as the energy works its way outward and the star's structure adjusts to its new internal reality. After the helium flash, the sun will settle into a new equilibrium, burning helium in its core while continuing to burn hydrogen in the shell around it. This phase of stellar life is called the horizontal branch, a reference to how such stars appear on certain astronomical diagrams. The sun will remain in this state for approximately 100 million years, a brief chapter compared to its 10 billion year main sequence lifetime, but still long enough for worlds to be transformed beyond recognition. During this phase, the sun's size will fluctuate. It will be larger than it is today, significantly larger, but smaller than it will eventually become. The planets will continue to orbit, their trajectories altered slightly by the sun's changing mass, because the sun will be losing mass throughout this process, shedding its outer layers into space through an increasingly powerful stellar wind. Mercury may already be gone by this point, engulfed during the sun's earlier expansion. Venus will be in peril. Earth's fate hangs in the balance, dependent on precisely how much the sun expands and how much mass it loses during the expansion. But the helium, like the hydrogen before it, is finite, and helium fusion produces ash of its own, carbon and oxygen accumulating in the core like embers in a dying fire. When the core helium is exhausted, the sun will face the same crisis it faced when the core hydrogen ran out. The core will contract, heat, and the fusion reactions will migrate outward into a helium-burning shell surrounding the carbon-oxygen core. Above that, the hydrogen-burning shell will continue its own work. The sun will possess 2 nested shells of nuclear fire, each converting lighter elements to heavier ones, each dumping energy into the layers above. This is when the sun will truly transform into something unrecognizable. The energy released by the double shell burning will drive a final dramatic expansion of the outer layers. The sun will swell beyond any size it achieved during its earlier giant phase, ballooning outward until it reaches a diameter of approximately 250 million kilometers, large enough to engulf Mercury's current orbit entirely, large enough to reach past Venus, and possibly to the orbit of Earth itself. The surface temperature will drop to around 3,000 degrees Celsius, cooler than many industrial furnaces, and the Sun's colour will shift to a deep, ruddy red. It will become a red giant in the fullest sense of the term, a star transformed almost beyond recognition from the stable yellow furnace we know today. Picture this transformation in terms you can hold in your mind. The Sun you see today, if reduced to the size of a basketball, would become a sphere roughly 250 times larger during the red giant phase, a sphere with a diameter of about 60 metres, tall as a 20-storey building. If you placed the current Sun at the centre of a football field, the red giant Sun would extend past the end zones, past the parking lots, past the surrounding streets, filling an entire city block with its bloated, dying bulk. The transformation is not merely quantitative, it represents a fundamental change in what the Sun is, from a compact, stable, hydrogen-burning star to an enormous, unstable, shell-burning monster in the final stages of its existence. The appearance of the red giant Sun from Earth's surface, assuming Earth survives and retains any surface from which to observe, would be beyond comprehension. The Sun would fill a quarter of the sky or more, a vast red wall of light hanging perpetually overhead, its edges fuzzy and indistinct where the tenuous outer atmosphere fades into the blackness of space. The light would be dimmer per unit area than the current Sun's light, but the sheer size would more than compensate. The total illumination would be intense, and the heat would be lethal. Earth's oceans would have boiled away long before this point. The atmosphere would have been stripped by the increasingly violent stellar wind. The planet would be a scorched, airless rock, if it remained a planet at all, rather than being vaporized entirely as the Sun's expanding surface reached outward to embrace it. This is not speculation. This is the mathematically inevitable consequence of the physics that governs stellar evolution. Every Sun-like star in the universe follows this trajectory. We have observed red giants throughout the Milky Way galaxy, ancient stars in the final chapters of their existence, and their properties match the predictions of stellar evolution theory with remarkable precision. The Sun's future is written in the light of countless other stars that have already walked this path. We merely await our turn. But the red giant phase is not the end. Stars like the Sun do not die in cataclysmic explosions. They lack the mass to generate the temperatures necessary for carbon fusion, which would require a core temperature of approximately 600 million degrees Celsius, far beyond what a star of the Sun's mass can achieve. The carbon-oxygen core will sit there, inert and compressed, while the double shell burning continues in the layers above it. The core will grow denser and denser as more ash accumulates, supported against further collapse only by the quantum mechanical pressure of degenerate electrons. And the outer layers will become increasingly unstable. Red giant stars in this phase experience dramatic pulsations, their surfaces expanding and contracting over periods of months to years. Each pulsation drives material outward, accelerating the stellar wind to prodigious rates. The Sun will begin shedding mass at thousands of times its current rate, streaming material into space in great billowing clouds. Over hundreds of thousands of years, these mass-loss events will strip away the Sun's outer layers entirely, exposing the hot, compressed core beneath. What remains when the outer layers are gone is a white dwarf, the exposed carbon-oxygen core of the Sun, roughly the size of Earth but containing approximately 60% of the Sun's original mass. This density is almost incomprehensible. A teaspoon of white dwarf material would weigh approximately 15 tons on Earth's surface. The entire mass of Mount Everest compressed into a volume the size of a sugar cube would approximate the density of white dwarf matter. Gravity at the surface would be crushing, tens of thousands of times Earth's surface gravity. An astronaut attempting to stand on a white dwarf would be flattened into a thin film of atoms within microseconds. The white dwarf will be hot when it first emerges from the shroud of expelled stellar material, perhaps 100,000 degrees Celsius at its surface, far hotter than the Sun's current 5,500 degree surface temperature. It will glow with a fierce bluish-white light, though its small size means its total luminosity will be far less than the current Sun's. The expelled outer layers, illuminated by this intense ultraviolet radiation, will glow in response, creating what astronomers call a planetary nebula, one of the most beautiful objects in the universe, a ghostly shell of gas surrounding a dying star, fluorescing in colours of red and green and blue depending on its chemical composition and temperature. The Helix Nebula, The Ring Nebula, the Cat's Eye Nebula. These are the dying breaths of stars like our Sun, spectacular cosmic memorials to stellar lives that have run their course. The Sun will create its own nebula when the time comes, and it will persist for perhaps 50,000 years before fading into the interstellar medium, its atoms dispersing to become the raw material for future generations of stars and planets. The white dwarf itself will endure far longer. With no internal energy source, it cannot shine through nuclear fusion. It glows only because of the residual heat trapped from its formation, heat that will slowly leak away into space over billions of years. The white dwarf will cool gradually, fading from blue-white to yellow to orange to red, its surface temperature declining century by century, millennium by millennium. After approximately 1 billion years, it will have cooled to perhaps 5,000 degrees Celsius, roughly the current temperature of the Sun's surface. After 10 billion years, it will have faded to a few thousand degrees. After 100 billion years, it will be nearly invisible, a cold, dark cinder drifting through the galaxy. This is the fate that awaits our Sun, a slow fade into darkness, a cooling corpse of carbon and oxygen that will persist essentially forever in the cold vacuum of space. No explosion, no rebirth, no second act, just an eternal cooling, an asymptotic approach to absolute zero that will never quite be reached. But before this ending, before the red giant expansion, before the white dwarf cooling, there are billions of years of gradual change that concern us more immediately. Because the Sun is not waiting until the distant future to change. It is changing right now, has been changing throughout its entire existence, and will continue to change in ways that will profoundly affect Earth long before the dramatic finale begins. The Sun is approximately 30% brighter today than it was when it formed 4.5 billion years ago. This gradual brightening is a direct consequence of the fusion process itself. As hydrogen converts to helium in the core, the average mass of the particles in the core increases. Helium nuclei are heavier than hydrogen nuclei. This change in composition causes the core to contract slightly, which heats it, which increases the rate of fusion, which increases the Sun's luminosity. The process is slow, roughly 1% brightness increase every 100 million years, but inexorable. This brightening poses a problem for life on Earth, a problem that operates on timescales long enough to be invisible to human civilization, but short enough to matter for the ultimate fate of the biosphere. As the Sun grows brighter, it delivers more energy to Earth's surface. Earth's climate system has feedback mechanisms that can compensate for modest changes in solar input. Weathering of silicate rocks, for instance, removes carbon dioxide from the atmosphere, cooling the planet. But these mechanisms have limits, and as the Sun continues to brighten over the coming hundreds of millions of years, those limits will be exceeded. Current models suggest that Earth has approximately 500 million to 1 billion years of habitable conditions remaining. This is not a precise figure. It depends on assumptions about climate feedbacks, about geological processes, about factors we may not fully understand. But the general trajectory is clear. The oceans will eventually evaporate. The atmosphere will become dense with water vapour, creating a runaway greenhouse effect that will sterilise the surface. Long before the Sun expands into a red giant, long before Earth faces the prospect of being engulfed by the swelling star, our planet will have been transformed into a Venus-like hellscape, too hot for liquid water, too hot for life as we know it. This fate is billions of years away. Civilizations rise and fall on timescales of centuries, species evolve and go extinct on timescales of millions of years, and even geological epochs span mere hundreds of millions of years. The window of habitability remaining to Earth is longer than multicellular life has existed on this planet. It is longer than any meaningful human planning horizon. In any practical sense, it is forever. And yet there is something profound in knowing that the story has an end, that the golden light streaming through your window each morning comes from a source that is slowly, imperceptibly, inevitably growing brighter, that will one day brighten past the threshold where life can persist. The Sun that nurtures us will eventually destroy us, not through violence, not through a sudden catastrophe, but through the simple, patient accumulation of light. The same fusion reactions that make life possible will eventually make life impossible. The gift and the curse are the same thing, separated only by time. This knowledge changes nothing about our daily lives. It changes nothing about the decisions we face as individuals, as societies, as a species. The sun will rise tomorrow morning regardless of what we know about its eventual fate. The crops will grow, the seasons will turn, the children will play in sunlight streaming through the same nuclear fires that have warmed every generation of humans who have ever lived. The physics operates on its own schedule, indifferent to our awareness of it. But there is value in understanding our position in cosmic time, in knowing not only that the sun sustains us now, but that it has sustained life for billions of years, and will continue to do so for hundreds of millions more. We are not living in the twilight of Earth's habitability. We are living in its long afternoon, with time enough for futures we cannot imagine, for transformations of life and intelligence that may eventually allow our descendants, biological or otherwise, to escape the fate of this particular world and carry the flame of consciousness elsewhere in the universe. The sun, in this sense, is not merely our sustainer but our deadline. It defines the window within which life on Earth must make something of itself, must evolve, must learn, must perhaps spread beyond the single world where it originated. 500 million years, a billion years, however long the window truly is, it is finite. And within that finite span, anything becomes possible. Species will arise and perish. Civilizations will rise and fall. The very concept of intelligence may transform beyond recognition as minds merge with machines or transcend physical form entirely. All of this lies within the span of the sun's remaining gift to Earth. The relationship between a planet and its star is the most fundamental relationship in any solar system. Everything else, moons, asteroids, comets, the vast emptiness of interplanetary space, exists within the context defined by the central star. The star's mass determines the orbits. The star's luminosity determines the climate. The star's lifetime determines the window within which life can evolve and flourish. Change the star, and you change everything that orbits it. We have examined one star in extraordinary detail, our own sun. We have launched spacecraft to study it, built telescopes to observe it, constructed mathematical models to predict its behaviour. We understand its structure from core to corona, its composition from element to element, its evolution from birth to death. This understanding represents one of the great achievements of human science, a triumph of curiosity and persistence and mathematical insight. We have taken the nearest star and rendered it comprehensible, but the Sun is one star among 200 to 400 billion in the Milky Way galaxy alone, and the Milky Way is one galaxy among at least 200 billion in the observable universe. The total number of stars that exist, or have existed, or will exist, exceeds any number the human mind can meaningfully grasp. Each of those stars is a fusion reactor, a source of light and heat, a potential anchor for orbiting worlds. Each of those stars follows the same basic physics that governs our Sun, the same equations of stellar structure and nuclear burning and gravitational equilibrium. The story we have told about our Sun is, in its fundamental outlines, the story of every Sun-like star in the universe. And orbiting some of those stars separated from us by distances so vast that their light takes years or centuries or millennia to reach us. There may be other worlds where other forms of life look up at other skies and wonder about other suns. They would see different colours depending on their star's temperature. Reddish light from cool dwarf stars, bluish light from hot giant stars. They would experience different day lengths, different seasons, different patterns of solar activity. But they would face the same fundamental situation we face, utter dependence on a nuclear furnace they did not choose and cannot control, a relationship of absolute vulnerability to a celestial object that will eventually either kill them or die itself. This universality is both humbling and connecting. The physics that makes life possible here makes life possible in principle, anywhere stars shine. The nuclear reactions in the Sun's core are the same reactions occurring in the cores of stars in the Andromeda Galaxy, 2.5 million light-years away. The helium produced by those distant reactions is the same helium produced in our own Sun. The carbon and oxygen being forged in the cores of red giants across the universe is the same carbon and oxygen that will one day constitute our Sun's white dwarf corpse. The elements do not differ from star to star. The equations do not change from galaxy to galaxy. Physics is universal, and so is the story of stars. The Sun, for all its staggering size and power, is in a sense typical. It is a G-type main sequence star, falling squarely in the middle range of stellar masses, neither massive enough to explode as a supernova, nor small enough to burn for trillions of years as a red dwarf. It is unremarkable except in one crucial regard: it is ours. This particular fusion reactor, orbited by this particular rocky world, illuminated the molecular processes that gave rise to life on this particular planet. The Sun's precise characteristics, its luminosity, its stability, its longevity, created the conditions within which everything we know and are could emerge. And those characteristics, seemingly perfect for the emergence of complex life, did not arise by chance or design. They are the inevitable consequences of the Sun's mass, set at the moment of its formation 4.6 billion years ago, when a cloud of interstellar gas began to collapse under its own gravity. That initial mass, one solar mass by definition approximately 2 nonillion kilograms, determined everything that would follow: the core temperature, the rate of fusion, the surface luminosity, the total lifespan, the eventual mode of death. Mass is destiny for a star, and our Sun's destiny was written in the gravitational contraction of a molecular cloud that had itself been seeded with heavy elements from the deaths of earlier stars. This is the cosmic recycling that makes Sun-like stars possible in the first place. The hydrogen and helium that dominate the Sun's composition are primordial, forged in the first few minutes after the Big Bang, when the universe was a hot, dense soup of particles and radiation. But the heavier elements that constitute the remaining 1.69% of the Sun's mass could not have formed in that primordial furnace. Carbon, nitrogen, oxygen, iron. These required the nuclear furnaces of stars, the intense pressures and temperatures found only in stellar cores and supernova explosions. The Sun, in other words, is made partly of stardust. It contains the ashes of stars that lived and died before our solar system existed. Stars that converted hydrogen to helium to carbon to oxygen to iron, and then scattered those products across interstellar space in violent deaths. We are accustomed to thinking of ourselves as made of stardust, and this is true. But so is the Sun. Every atom of calcium in your bones was forged in a star. Every atom of iron in your blood was forged in a star. And every atom of iron in the Sun's core, participating in the energy transport processes that ultimately make your existence possible, was forged in an earlier star as well. The Sun is a second-generation star at minimum, possibly third or fourth generation, carrying within its mass the accumulated nuclear products of billions of years of stellar evolution. This ancestry connects our Sun to a vast network of stellar genealogy extending back to the very first stars that formed in the universe. Those first stars, the so-called population 3 stars, contained no heavy elements whatsoever. They were pure hydrogen and helium, formed from the pristine material of the early universe, and they were almost certainly massive, perhaps hundreds of solar masses, because the absence of heavy elements meant the gas could not cool efficiently, and inefficient cooling meant only large masses could collapse and ignite fusion. Those first stars burned hot and bright and brief, living perhaps only a few million years before exploding as supernovae and spreading their nuclear products across the cosmos. The heavy elements they created allowed the next generation of stars to form more easily, and those stars in turn created and dispersed more heavy elements when they died. Generation after generation, the universe became increasingly enriched with the building blocks of rocky planets and complex chemistry and eventually life itself. The Sun is a late entry in this grand sequence, forming approximately 9 billion years after the Big Bang in a region of space already rich in heavy elements. This timing was not merely fortunate, it was necessary. Had the Sun formed too early, the heavy element abundance would have been too low to create rocky planets like Earth. Had it formed too late, the conditions might have been different in ways we cannot fully predict. The Sun formed in a Goldilocks epoch, when the galaxy had accumulated sufficient heavy elements to enable Earth-like planets, but had not yet evolved past the point where such systems could persist. And the Sun formed in a Goldilocks location, far enough from the galactic centre to avoid the intense radiation and gravitational disruptions of that crowded region, but not so far out that heavy elements were scarce. The Sun's position in the Milky Way, approximately 26,000 light-years from the galactic centre, places it in what astronomers sometimes call the galactic habitable zone, a ring of relative calm where stellar collisions are rare, radiation levels are manageable, and the chemical ingredients for rocky planets are abundant. None of this was inevitable. The molecular cloud that collapsed to form the Sun might have fragmented differently, producing several smaller stars or one larger star. The timing might have been off by tens of millions of years, which sounds like a long time but is nothing on cosmic scales. The location might have been different, closer to the galactic centre, where passing stars could have disrupted the young solar system's orbital architecture, or closer to a region of active star formation, where supernova explosions could have sterilized any developing life. The Sun we know, with its precise mass and composition and galactic position, represents one outcome among countless possible alternatives, most of which would not have led to anything resembling Earth or humanity. We exist because a particular molecular cloud collapsed in a particular way, in a particular place at a particular time, and the star that resulted happened to have characteristics compatible with the long, slow emergence of biological complexity on an orbiting rocky world. This specificity should give us pause. The Sun is not merely large or powerful or ancient. It is precisely calibrated, not by any external intelligence, but by the relentless logic of physics, to produce the conditions we require. A star 10% more massive would have a significantly shorter lifespan and higher ultraviolet output. A star 10% less massive would be dimmer and cooler, requiring planets to orbit much closer to achieve liquid water temperatures, which would likely result in tidal locking and a host of other complications. The Sun sits in a sweet spot, and while this sweet spot is not vanishingly narrow, there are billions of Sun-like stars in the galaxy. It is also not infinitely broad. The universe does not guarantee the existence of stars like ours. It merely permits them under the right circumstances, and we happen to orbit one. The recognition of this contingency transforms how we should think about the Sun. It is not simply a given, a fixture of the sky as permanent as the mountains. It is a specific object with a specific history and a specific future, an object that happened to form in a way that made our existence possible. The small yellow disk we see in the sky is not a symbol or an abstraction. It is a real thing, a physical object, a ball of plasma undergoing nuclear fusion at a rate of 620 million metric tons of hydrogen per second. Every photon that strikes your retina was born in that furnace, travelled 8 minutes and 20 seconds through the vacuum of space, entered Earth's atmosphere, and arrived at your eye carrying information about the star's surface temperature and chemical composition. You are in a direct physical relationship with the Sun every moment of every day, bathed in its radiation, warmed by its energy, seeing by its light. The Sun is not distant. It is intimate, woven into every aspect of your existence, in ways both obvious and invisible. Consider what it means to stand in sunlight. The warmth you feel on your skin is infrared radiation, electromagnetic waves with wavelengths between 700 nanometers and 1 millimeter, absorbed by molecules in your outer layers and converted to thermal energy. This is not a metaphor. This is heat transfer, the same process that occurs when you stand near a campfire or a radiator. The Sun is heating you from 93 million miles away with sufficient intensity that you can feel it clearly. On a summer day, the solar flux reaching Earth's surface can exceed 1,000 watts per square meter, roughly the power output of a small microwave oven, concentrated on every square meter of sunlit ground. If you are outdoors on a cloudless summer noon, you are receiving enough solar energy to power significant electrical appliances, delivered for free by a fusion reactor 8 light minutes distant. The visible light component of that solar flux enables sight. Your eyes evolved to detect electromagnetic radiation in the range of roughly 400 to 700 nanometers, because that is the range in which the Sun emits most intensely. This is not coincidence. Eyes evolved under solar illumination, and natural selection optimized them for the available light. If the Sun were significantly hotter, emitting primarily in the ultraviolet range, our ancestors would have faced strong selective pressure to develop ultraviolet-sensitive vision or to remain nocturnal. If the Sun were significantly cooler, emitting primarily in the infrared, heat-sensing organs might have become the dominant visual apparatus. The fact that we see in colour, that we perceive the world in shades of red and green and blue, is a direct consequence of our star's surface temperature. The rainbow exists because the Sun exists as it does. The entire visual aesthetic of Earth, the blue of the sky, the green of vegetation, the gold of wheat fields, the white of clouds, emerges from the interaction between solar light and terrestrial matter under our particular stellar regime. Plants, of course, take this interaction further. Photosynthesis captures solar photons and uses their energy to drive the chemical reactions that convert carbon dioxide and water into sugars and oxygen. The glucose your body burns for energy, whether derived from bread or fruit or meat, traces its origin to captured sunlight. Every calorie you consume is stored solar energy, transformed through biological processes, but ultimately traceable to photons that left the sun's surface minutes before they struck a leaf. When you eat, you are eating sunlight. When you move, you are powered by sunlight. When you think, the electrochemical processes in your neurons are fueled by sunlight, processed through the remarkable machinery of metabolism. The sun is not merely above you, it is within you, converted to chemical form and incorporated into your very tissues. This incorporation is literal, not poetic. The atoms in your body were assembled using solar energy. The bonds holding your DNA together are maintained by metabolic processes that require constant energy input, energy that comes, always and ultimately, from the sun. If the sun were to vanish, the immediate consequence would be darkness and cold, but the slower consequence would be the cessation of all biological activity on Earth. Plants would die within weeks, herbivores would follow within months, predators soon after. Even organisms living near deep-sea hydrothermal vents, seemingly independent of solar energy, depend indirectly on a biosphere that the sun created and sustains. The oxygen they breathe was produced by photosynthesis. The organic matter that rains down from the surface to feed deep-sea ecosystems originated in the sunlit zone. Remove the sun, and the entire intricate web of terrestrial life unravels, leaving a frozen, dead world orbiting through the darkness. This absolute dependence creates a strange paradox in human psychology. We take the sun for granted precisely because it is so essential. It rises every morning, sets every evening, and provides the light and warmth we need without any effort on our part. We do not have to tend the sun, repair it, refuel it, or protect it. It simply works day after day, year after year, century after century. This reliability breeds complacency. We forget that the sun is not a service but a phenomenon, not a resource but an event. It is happening right now. Nuclear reactions, convective churning, magnetic field generation, coronal heating, all of it occurring continuously, all of it indifferent to our existence, all of it far beyond our control or comprehension in any practical sense. The science we have developed to understand the sun is remarkable, but it should not be confused with mastery. We can predict solar eclipses to the second. We can model the solar interior with impressive accuracy. We can forecast space weather with increasing skill, but we cannot change the sun. We cannot adjust its output, modify its magnetic cycle, or extend its lifespan. We are observers and beneficiaries, not participants. The sun will do what the physics dictates, and we will adapt or perish accordingly. This is a humbling realization for a species that has grown accustomed to reshaping its environment. We have dammed rivers, levelled mountains, and altered the composition of the atmosphere. But the sun remains utterly beyond our reach, a reminder that some forces in the universe do not yield to human ambition. And yet, this same science has given us something precious: understanding. We know what the sun is. We know why it shines. We know how it was born, how it lives, and how it will die. This knowledge does not give us power over the sun, but it gives us something almost as valuable: perspective. We can situate ourselves in cosmic context, understanding our place in the stellar life cycle, the galactic ecosystem, the universal narrative of matter and energy transforming across billions of years. The sun is not mysterious, it is knowable, and in knowing it, we come to know ourselves as products of stellar evolution, temporary arrangements of matter animated by stellar energy, brief witnesses to a cosmic process that began long before we existed and will continue long after we are gone. The sun has burned for 4.6 billion years. It will burn for another 5 billion years before exhausting the hydrogen in its core and beginning the long, slow transformation into a red giant. During that time, it will continue to warm Earth, drive weather patterns, power photosynthesis, and enable the biosphere in which we are embedded. Whether humans will exist to witness the sun's later stages is uncertain. 5 billion years is an almost inconceivable span, long enough for evolution to produce countless new species, long enough for continents to rearrange themselves multiple times, long enough for asteroids to impact and ice ages to come and go, and civilizations to rise and fall without number. What we can say with confidence is that the sun will persist, indifferent to whatever dramas unfold on its planets, steadily converting mass to energy, according to the equations Einstein wrote down in 1905. That conversion, mass to energy, matter to light, is the fundamental transaction of stellar existence. The sun is slowly consuming itself, trading its substance for the radiation that makes life possible. Every second, 620 million metric tons of hydrogen becomes 616 million metric tons of helium, and 4 million metric tons of mass vanish, transformed into energy according to E equals mc squared. This is not a metaphor. The sun is literally getting lighter. It weighs slightly less now than it did when you began reading this sentence. The mass difference is converted to gamma rays in the core, which are absorbed and re-emitted countless times during the long journey to the surface, finally emerging as the visible light and infrared radiation we perceive as warmth and brightness. What reaches your skin is the converted mass of the sun, matter transformed into energy, transformed into sensation. This process has been ongoing for billions of years and has already converted a significant fraction of the sun's original hydrogen into helium. The helium accumulates in the core, inert and dense, the ash of nuclear burning. As the helium fraction increases, the hydrogen-burning shell must move outward to find fresh fuel, and the core slowly contracts and heats. These changes are gradual on human timescales, but inexorable on cosmic timescales. The sun is not static. It is evolving, changing year by year and century by century, becoming gradually brighter and hotter as it ages. The sun that shone on the dinosaurs was about 1% dimmer than the sun that shines on us. The sun that will shine on whatever organisms exist a billion years from now will be 10% brighter than today. These changes matter. A 10% increase in solar luminosity will significantly alter Earth's climate, potentially pushing surface temperatures beyond the range compatible with liquid water. Life on Earth may have only a billion years remaining, not 5 billion, because the sun's increasing brightness will eventually sterilize the planet even before the red giant phase begins. This future is written in the physics of stellar evolution. The sun will brighten, Earth will warm, the oceans will evaporate, the atmosphere will be stripped away, and the planet that gave birth to the most complex structures in the known universe will become a scorched, lifeless rock orbiting a swollen red star. This is not speculation. This is prediction, based on well-understood physics and observations of countless other stars at various stages of evolution. We know what happens to stars like the sun because we have seen it happen elsewhere in the galaxy. The sun's fate is not a mystery, it is a certainty, deferred by time but ultimately inescapable. And yet, knowing this fate does not diminish the sun. If anything, it enhances the preciousness of the current moment, the cosmic instant in which the sun's output and Earth's orbit and the emergence of intelligent life happen to coincide. We exist in a window, a brief opening in cosmic history when conditions are right for beings like us to emerge and wonder about beings like us. The sun created this window. The sun will eventually close it. Everything we do, everything we think, everything we hope for occurs within the span of stellar tolerance, permitted by a nuclear furnace that does not know we exist and would not care if it did. This indifference is not cruelty. It is simply physics. The sun has no intentions, no preferences, no awareness. It is a ball of plasma undergoing thermonuclear reactions, nothing more and nothing less. The meaning we find in sunlight, the beauty we perceive in sunsets, the life we derive from solar energy, these are our interpretations, our additions to a cosmic process that proceeds without purpose. The sun does not shine for us. It shines because fusion reactions release energy, and energy must go somewhere. That some of that energy happens to sustain complex chemistry on a nearby rocky planet is, from the sun's perspective, if the sun could have a perspective, entirely incidental. But from our perspective, everything depends on that incidence. The entire human story, from the first hominids walking upright on the African savanna to the spacecraft we have sent to orbit other worlds, unfolds under the light of this particular star. Every civilization that has ever existed has risen and fallen while the sun burned steadily overhead. Every religion has incorporated the sun into its mythology, recognizing intuitively what science has confirmed literally. We are utterly dependent on this celestial object, and our fate is bound to its physics. The Egyptians worshipped Ra, the Greeks honoured Helios, the Aztecs sacrificed to Tonatiuh. These were not foolish superstitions, but reasonable responses to an obvious truth. The sun is the source of life, and life owes the sun acknowledgement. Modern science has not diminished this truth, it has deepened it. We know now that the sun does not merely warm and illuminate, it drives atmospheric circulation, ocean currents, the water cycle, the carbon cycle. It powers the photosynthesis that oxygenated our atmosphere and enabled the evolution of animals. It created the fossil fuels we burn and the wind and solar energy we are learning to harvest. It generates the space weather that threatens our technology and the magnetic field interactions that create auroras. The sun is not one thing in our lives. It is everything in our lives, the central axis around which terrestrial existence rotates both literally and figuratively. The monster in the sky has been with us since before there was an us, since before there was life, since before there was Earth. It watched the formation of the planets from the debris disk of its own creation. It witnessed the late heavy bombardment when asteroids and comets rained down on the young inner planets. It illuminated the first oceans, the first microbes, the first photosynthetic organisms that began to transform the atmosphere. It has been the one constant through all of Earth's history, the fixed point around which everything else has changed. Continents have formed and split and collided and reformed. Species have appeared and flourished and gone extinct. Ice ages have come and gone and come again. Through it all, the sun has burned, stable and reliable and unimaginably powerful, a guarantor of continuity in a world of endless change. And now we stand at a peculiar moment in that long continuity, a moment unlike any that has come before. For the first time in 4.5 billion years of solar history, something on one of the sun's planets has begun to understand what the sun actually is, not merely to worship it, not merely to track its movements across the sky, not merely to plant crops according to its seasons, but to comprehend the nuclear physics of its core, to measure the neutrinos streaming from its fusion reactions, to predict its behaviour centuries in advance, to send spacecraft into its outer atmosphere and return data about the conditions there. We are the first beings in this solar system capable of genuine solar comprehension. Every dinosaur that ever lived basked in sunlight without the slightest understanding of where that warmth originated. Every trilobite that swam in Cambrian seas 500 million years ago responded to solar-driven temperature gradients without knowing what the sun was made of. Every bacterium that has ever performed photosynthesis has captured solar photons without grasping that those photons began their journey in a fusion reaction, converting hydrogen to helium. Only we have made that conceptual leap. Only we have moved from experiencing the sun to understanding it, from passive reception to active comprehension. This is not a small thing. This is not a trivial achievement to be catalogued alongside other human accomplishments. This is, in a very real sense, the universe becoming aware of itself. The sun is made of hydrogen and helium and trace heavier elements. Humans are made of carbon and oxygen and nitrogen and hydrogen, atoms forged in stars like the sun, or in the explosive deaths of stars larger than the sun. We are stellar material contemplating stellar material. We are fusion products studying fusion processes. When a human scientist calculates the rate of proton-proton chain reactions in the solar core, there is a profound circularity at work. Atoms that were once inside stars are now thinking about how atoms behave inside stars. The sun did not create life in order to be understood, but life emerged anyway, and understanding followed, and now the solar system contains something that can look back at its star and grasp what it is seeing. The monster has been observed. The monster has been measured. The monster has been, in some limited but genuine sense, known. Consider what that knowledge cost us, what effort and ingenuity and accumulated insight were required to reach this point. The ancient Greeks knew the sun was far away because it showed no parallax as the earth moved, but they could not say how far. They knew it was large because it appeared the same size as the moon during eclipses while clearly being more distant, but they could not calculate its true diameter. They knew it was hot because its light warmed the Earth, but they could not imagine temperatures in the millions of degrees. Each piece of solar knowledge we now possess represents centuries of intellectual struggle, false starts, abandoned theories, refined instruments, mathematical breakthroughs. Copernicus placed the sun at the centre of the solar system, but had no idea what the sun was made of. Newton calculated the gravitational influence the sun exerted, but could not explain why it shone. 19th century physicists knew the sun could not burn chemically, and suggested gravitational contraction as its energy source, a theory that gave the sun a lifespan far too short to account for geological evidence of Earth's age. Only in the 20th century, with the discovery of nuclear fusion and the development of quantum mechanics, did we finally understand the solar engine. And only in the late 20th and early 21st centuries have we developed the technology to study that engine directly, to send probes into the solar wind and measure conditions that would vaporize any physical object in seconds. This accumulated knowledge transforms how we must think about our relationship with the sun. The ancients saw the sun and created gods. The medievals saw the sun and calculated orbits. The moderns see the sun and recognize a natural phenomenon operating according to physical laws. But that recognition does not diminish the sun's significance. If anything, understanding the sun scientifically makes it more awesome, not less. A god that grants life is impressive in the way that imaginary beings can be impressive. A thermonuclear reaction that grants life is impressive in a way that only real things can be. It is actually happening, right now, and the numbers that describe it are too large to hold in the human mind without training. The sun is not supernatural. It is natural, and nature, properly understood, is more staggering than any mythology ever dreamed. Think about what it means that the sun is natural, that it operates according to the same physics that governs everything else in the universe. It means that the sun is not unique. It means that the processes creating solar energy are the same processes occurring in every other star in the observable universe. The Milky Way contains somewhere between 100 billion and 400 billion stars, most of them burning hydrogen in their cores just as our sun does. The observable universe contains approximately 2 trillion galaxies. If each galaxy averages 100 billion stars, that gives us something like 200 sextillion stars, 2 followed by 23 zeros, each one a thermonuclear furnace, each one releasing energy through the same fusion reactions that power our local star. The sun is not special, it is ordinary. It is a typical G-type main sequence star, middle-aged, medium-sized, unremarkable by astronomical standards, and yet to us it is everything, the one star among sextillions that happens to be close enough and stable enough and long-lived enough to have permitted our existence. This ordinariness is itself profound. The same physics that works here works everywhere. The same fusion reactions that sustain terrestrial life could, in principle, sustain life elsewhere. If the sun is ordinary, then sun-like stars are common. If sun-like stars are common, then planets in the habitable zones of those stars may be common. If such planets are common, then the conditions that permitted life to emerge on Earth may have been replicated billions of times throughout cosmic history. We do not know whether life exists elsewhere. We do not know whether intelligence exists elsewhere. But we know that the physics permits it, that the universe is not hostile to the emergence of complexity, that stars like our sun could, in principle, nurture worlds like our Earth. The monster in our sky is one of countless monsters scattered throughout the cosmos, each one a potential source of light and warmth and energy for whatever might orbit nearby. The universe is full of suns. We happen to live near this one, but we do not merely live near it. We are, in a deep sense, made of it. The heavy elements in your body, the calcium in your bones, the iron in your blood, the phosphorus in your DNA, were not created in the sun. They were created in previous generations of stars that lived and died before the sun was born. When a massive star exhausts its nuclear fuel and explodes as a supernova, it scatters newly forged heavy elements into the interstellar medium, seeding future star-forming regions with the raw materials for rocky planets and organic chemistry. The sun formed from a cloud of gas and dust that was itself enriched by such supernova debris. The planets that coalesced around the young sun inherited that enrichment. We are quite literally made of stardust, our bodies assembled from atoms that were once inside stellar cores, where temperatures reached billions of degrees, and pressures crushed matter into exotic states. The sun did not create those atoms. but the sun gravitationally organised them, drawing together the debris disk from which Earth formed, providing the energy that drove the chemical reactions from which life emerged, maintaining the stable conditions that allowed evolution to operate over billions of years. The sun is our parent star in more than a poetic sense. We are its descendants, the products of its patient and indifferent nurturing. And what have the sun's descendants done with their inheritance? We have spent most of our existence simply surviving, eking out livings from the solar-powered biosphere, hunting and gathering and eventually farming the solar-grown plants that sustained our growing numbers. Only in the last few centuries have we begun to understand our situation, to grasp the cosmic context in which we exist. Only in the last few decades have we developed the technology to examine the sun directly, to send instruments into its domain, to capture images of its surface in wavelengths our eyes cannot perceive. The Parker Solar Probe, launched in 2018, has flown closer to the sun than any previous spacecraft, passing within 4 million miles of the solar surface and returning data about the solar wind that was impossible to obtain from Earth. The Solar Dynamics Observatory, launched in 2010, has been watching the sun continuously in multiple wavelengths, capturing every flare, every coronal mass ejection, every evolution of the magnetic field. The Daniel K. Inouye Solar Telescope in Hawaii, the largest solar telescope ever built, has imaged the solar surface in unprecedented detail, revealing the cell-like patterns of convection with a resolution that shows features as small as 18 miles across. We are studying the monster with instruments the monster cannot damage, building knowledge that will allow us to predict the monster's behaviour and protect ourselves from its tantrums. This is not arrogance. This is not the hubris of creatures overreaching their station. This is the natural consequence of having evolved intelligence in a universe governed by comprehensible laws. The sun is not angry that we study it. The sun does not resent our probes or our telescopes or our mathematical models. The sun continues to burn, indifferent to our investigations, converting 600 million tons of hydrogen into helium every second, regardless of whether anyone is watching. Our understanding changes nothing about the sun, but it changes everything about us. It changes what we know, what we can predict, what we can prepare for. A civilization that understands stellar physics is different from a civilization that worships stellar gods. Not better, necessarily, but different, operating with different assumptions and different capabilities. We cannot appease the sun with sacrifices, but we can model the sun with equations, and those equations give us power the Aztec priests never possessed. The power to anticipate coronal mass ejections, to shield our electronics, to plan our space missions around solar cycles, to build structures that can withstand solar radiation. There is something humbling about this power. We have learned enough about the sun to know how little we can do about it. We cannot turn down the thermostat. We cannot adjust the fusion rate. We cannot alter the orbit we occupy or the output we receive. We can only adapt, only protect, only prepare. The sun will continue to brighten, and we will either develop the technology to cope or we will not. The sun will eventually exhaust its hydrogen and expand into a red giant, and we will either have left by then, or we will perish with the planet that birthed us. The sun sets the terms, we work within them. This is not slavery. It is simply the nature of existence for a planetary civilization dependent on its host star. Every civilization that might exist around every star in the universe faces the same constraints, the same ultimate dependence, the same need to adapt or die. Perhaps this is the deepest lesson the sun has to teach us. We are powerful in some ways and powerless in others. We can build rockets that escape Earth's gravity, but cannot escape the sun's influence. We can split atoms and fuse them, but cannot match the sun's output with all our technology combined. We can extend human lifespans by decades, but cannot extend the sun's lifespan by a single day. There are limits to what intelligence can achieve, boundaries set by physics that no amount of ingenuity can transcend. The sun reminds us of those limits simply by being what it is, a fusion reactor so vast that all human industry is trivial beside it, a timekeeper so slow that civilizations are mayflies in comparison, a gravitational anchor so massive that we will never escape its domain without extraordinary effort. The monster does not threaten us deliberately. It threatens us structurally, inherently, by being so much larger and more powerful than we can currently match. But within those limits, within the boundaries the sun has set, the possibilities remain enormous. We have existed as a technological species for perhaps 3 centuries, a bare eye blink in solar time. We have sent spacecraft throughout the inner solar system and probes to the outer planets. We have walked on the moon, a body visible only because it reflects sunlight. We have built telescopes that can see galaxies billions of light years away, other stars hosting their own planets, hosting, perhaps, their own intelligences wondering about their own suns. In 3 centuries we have gone from Newtonian mechanics to quantum field theory, from wooden ships to spacecraft capable of surviving passage through the solar corona. What might we achieve in another 3 centuries, another 1,000 years, another 1,000,000 years if the sun continues to shine and we continue to adapt and grow? The sun will give us that time. Barring catastrophe, barring self-destruction, the sun will continue to provide the energy necessary for technological civilization for hundreds of millions of years. The warming will be gradual enough that advanced technology could compensate, moving populations, adjusting agriculture, perhaps eventually geoengineering on a planetary scale. The sun will not fail us suddenly. It will change slowly, predictably, according to equations we already understand. We have time if we use it wisely. We have energy if we harvest it intelligently. We have knowledge if we continue to pursue it. The monster is not our enemy. The monster is our context, our constraint, our opportunity. The monster is the central fact of our existence, and learning to live with it, not merely beneath it, but with it, in full understanding of what it is perhaps the essential task of our species. Look up at the sun tomorrow. Not directly, never directly, but in the early morning when it rises or the late evening when it sets, when the atmosphere dims its light enough to glimpse without danger. Try to see it not as a small yellow disk, comfortable and familiar, but as what it actually is. Try to feel the 93 million miles between you and that light, the 8 minutes and 20 seconds it took for those photons to reach your eyes. Try to imagine the convection cells the size of Texas churning the solar surface, the sunspots larger than Earth rotating into view, the coronal mass ejections hurling billions of tons of plasma into space. Try to comprehend that what you see is only the photosphere, the thin, visible layer atop an inferno that descends toward a core where temperatures reach 27 million degrees Fahrenheit and pressures crush matter into conditions found nowhere else within billions of miles. You will not succeed. Not fully, not completely. The sun resists comprehension by its very nature, but the attempt matters. The effort to understand, even when understanding is partial, is what distinguishes us from every other species that has ever basked in solar warmth. The dinosaurs could not wonder about the sun. The trilobites could not calculate its mass. Only we can look up and ask what we are seeing and struggle toward an answer and be awed by how much the answer exceeds our expectations. The sun is not what you think it is. The sun is more, always more, a monster hiding in plain sight that reveals new depths of monstrosity the closer we look. And somehow, through the patient accumulation of human insight across centuries, we have begun to glimpse the monster's true face. That glimpse is our inheritance and our responsibility. We are the species that looks at the sun and understands. We are the descendants of creatures who emerged in sunlight and evolved in sunlight and built civilizations in sunlight, and now we know what sunlight is, where it comes from, how long it will last. This knowledge connects us to the past, to every human who ever wondered about the glowing disk in the sky, and to the future, to every human who will continue that wondering until the wondering stops. The sun does not care about this connection, but we can care. We can recognize that understanding the sun is one of humanity's great achievements, a triumph of collective intelligence that spans cultures and centuries and continues today in observatories and spacecraft and physics departments around the world. The monster that sustains us will one day destroy the world that we know. This is certain, written in the equations of stellar evolution, unavoidable by any technology we can currently imagine. But between now and then lies an expanse of time so vast that it contains more possible human futures than we can enumerate. In that time, under that sun, with the energy that the sun provides, we will either flourish or fail, expand or contract, transcend our limitations or succumb to them. The sun does not determine our choices, it merely illuminates them. It provides the light by which we see, the warmth by which we live, the energy by which we work, and then it leaves the rest to us. What will we do with this borrowed fire? What will we build in the long afternoon of solar stability that remains? What will we become under the unwavering gaze of a star that has watched us emerge from simplicity into complexity, and now waits, without patience, without impatience, without any quality that implies awareness, to see what we do next? The sun has no answers to these questions. The sun has no questions. The sun simply burns, as it has burned for 4.5 billion years, as it will burn for billions more, steady and reliable and vast beyond human reckoning. The meaning we make of that burning is our own. The stories we tell about that light are our own. The futures we build under that warmth are our own to construct. Look up. The monster is there, as it has always been, as it will be long after the last human has drawn the last breath. But you are here too, one brief arrangement of solar-forged atoms that has somehow learned to turn back toward its source and wonder. That wondering is rare in the universe. That wondering may be precious beyond measure. The sun does not care, but you can, and perhaps that is enough.